Hi, welcome back. It's Tuesday. I'm on a quest for the Quintic, and today is going to be mostly Galois theory. This is a maths live stream where I attempt to learn mathematics while live streaming the whole thing, so that it keeps me honest. Let's just check that I've connected things correctly. Have I unmuted? Yes. Is that connected to anything? Yes, it is. Oh, there we go then. Right, great. Okay, it's 9 o'clock in the UK. Feels very early, but that's just how jobs work. Right, okay. Here's the map for the quest, as always. Hi, morning, Filsey. You don't have to catch up. Oh my goodness. It's like 7 hours a day. That's way more. It's my entire life. But nice to see you this morning. Hi. Here's the map. Here's how far we got on our quest so far. We started out here in the happy spaces of group theory and vector spaces, and then we went through this kind of mountain range of ring theory. We learned about lots of different sorts of rings, and we've got as far as field extensions. But later on in our quest, we're going to have to go through the kind of wilds of Mordor over there, which is the place where the splitting fields and radicals and quintics live. I'm going to try and be a bit more disciplined today, I think. Yesterday I got bogged down in lots of the details of proofs, and I think the right thing to do with the Galois theory stuff is to get an overview first, to read through without looking at the proofs, which is very tricky as a mathematician, not to ask immediately why things are true, but I want to get a sense of what's there before going back and understanding why things are true. Essentially, I think my map is not very good around here, and I want to get a bit more map detail. So that's the plan for this morning, at least, is to try and find more detail around here about what's going on in Galois theory. Have some notes about what's going on, and then I guess this afternoon it's going to be start trying to fill in the details. Is my rough plan. I'm imagining there'll be a lot of stuff this morning that I don't understand at all. I'm kind of looking forward to it. The stuff that I don't understand is why I'm here. It's why anybody's learning maths, right? You want to look at stuff that you don't know. Okay, I've put the little stick figure here. I'm feeling like that's over ambitious, but we'll find out. Okay, so quick bit of housekeeping. I'm using for my Galois theory these notes, which I got from the Oxford website. Here's a scary page about finite filtrations that we looked at the end of yesterday. I got these from the Oxford website, and they're due to Damien Rossler. Asterisk, Damien Rossler's address. Great, sorry, I thought I'd show you the footnote as well. So if you want a copy of these lecture notes as well, maybe you get annoyed by me flipping around the pages quite a lot, or you just want to learn this not through Twitch, then you can get a copy off the Oxford website. The fastest way to get to it is to go to my Twitch page, click on homepage to get to my homepage, and then I've put a direct link there to these notes and to the rings notes that I was using yesterday. That's the plan. Ooh. 7 hours of talking, you say? Yeah, I could probably do that. Seems entirely sensible. Right, good. Okay. Let's have a quick look at the contents to see what we're in for today. The contents is in red, which is quite nice, I suppose. There's some preamble at the start, which I should read. There's some rings and domains. So we're happy because rings, domains, rings and fields, actions. So this stuff overlaps with yesterday. So 6 pages, hooray. I guess kind of 8 pages, we're going to be fine. Actions of groups on rings might slow me down a little bit because I'm going to have to remember about group actions. It's been, oh gosh, it's been about 12 years since I had to learn what an action on a group was. So at some point this morning, I'm going to learn that again. So that gets a little exclamation mark. And then field extensions. We had a little bit of field extension stuff yesterday. On the map there, the lava pit that we need to get through, I suppose. We had a definition, which helps us a little bit, but we've got all of this new stuff. Splitting fields, simple extensions, separability, normal extensions, which is all very new. So this stuff happy, this stuff exclamation mark, this stuff 2 exclamation marks. And then finally we get to Galois content. So it's going to take a while to get there. But when we're at Galois, then we're getting really close on our quest. Because that's where we learn some really good stuff. There is an overview, something called Arten's Lemma, which I think comes from a book by Arten, which somebody recommended to me for, not quite for this stream, but for general learning. So you might have to go and look at a book at some point. The fundamental theorem, this stuff sounds really good. I don't know what the theorem of the primitive element is at all. Section 5, I happen to know Section 5 is going to be really useful for the actual thing we're trying to do. So all of this gets 12 pages, this big chunk of sort of lots of stuff that we don't know at the moment. But then finally we get down to some group stuff. So near the Quintic mountain that we're reaching, trees and forest again, we get back to group theory. We've got to learn some group facts, which gets 1 exclamation mark, but then we get finally down to, there it is, insolvable quintics, which is what we came for. It's what we want. We're on the quest for the quintic. There is the fundamental theorem of algebra, which yesterday Elrud in chat showed a real interest in. So a stretch goal for the live stream is to read 2 pages about the fundamental theorem of algebra. I wasn't that bothered, but then a viewer yesterday was very keen. So we'll see. Okay. Let's try and put some of these on the map, maybe? I mean, these are the section titles. So, where do we want to put these? Why are solvable? So solvable groups are there, but I feel like we also saw them. Oh no, maybe this is other group facts. There's solvable groups. Radicals are in there. The radicals are on my map. Radical extensions. I'm going to go cyclotomic radical. It needs to be on the map. Cyclotomic. Okay, so these are like, what are these? Cyclotomic. So this bit needs a bit more definition over here. These are like small mountains, I suppose. Jagged rocks. They look like capital M's. Oh well. Cyclotomic extensions. Kummer extensions. And radical extensions. Let's try a little bit more like mountains. No, just look like really bold M's. Bold spotty M's. Fine. Okay, we've got a kind of plan. Had terrible handwriting over that side of the map, but I guess it is stressful being that close to the Quintic. We've got a plan for what the ends looks like. What was this bit in between? There's some stuff on Galois extensions. Actually, we've got Galois theory on the map, so that's good. Okay. So I'm going to do this. So these notes go rings, fields, Galois, complicated extensions, quintics. And I'm going to try and go through and not get too distracted by reading those like 4-line proofs. There was 2 or 3 moments yesterday where something had a proof that was about 4 lines long and it took about 20 minutes to understand, which slows down pacing if you're trying to get the big picture. So today I think I need to just go through 40 pages of notes. It's just 40 pages of notes, right? I'm trying to get out definitions and statements. That's fine. Okay, preamble. These are accompaniment to lecture notes. Read by Everest Galois. Good, okay. Austrian mathematician Artan. Approach to Galois theory. Most modern courses and textbooks. History. History is very important. Vice forms published by okay, great. There's some references, more books. Ooh, I could get Artan's lecture notes. Okay, interesting. Bare outline of the theory. Okay, right, fine. Probably not for typos. Here's the basic idea. I always like a basic idea. Good. So we know what some of these symbols mean from yesterday. So let P be a polynomial with rational coefficients. These are alphas are the complex roots, and let F be Q, and then I guess this is like a field extension, but using round brackets instead of square brackets. Fine. Subset of C be the smallest subfield of C. Ooh, maybe it's not a field extension. No, maybe it is. Yeah, maybe it is. Smallest subfield of C which contains these. C's a field, so a subfield. Fine, okay, take those elements. And they're inverses and real multiples? No, yeah, real multiples, not complex multiples, because that would be everything. Rational multiples? Gosh. Anyway, subfield is smallest subfield. How would you make it a field? Oh, you need to be able to add. There's no multiples of multiples by things is rules for ideals. That's not rules for fields. Yeah. Okay. Wake up. Oh, coffee. What am I thinking about with fields and multiplication? Thinking about vector spaces. That's not what a field is. Right. Good. Okay. What's my mental image for this then? I guess I've got these like alpha 1, alpha 2, alpha 3 origin. And those are my roots. I guess the roots are complex conjugates, so it's something more like origin. And my roots are maybe here, here, here. And I'm considering Q adjoined with those things to be the smallest subfield of C which contains those. So to try and build a field, is that like building a lattice out of these points? Guess so. If you've got a root here, then you build. So the field would include not multiples of those, but sums. That one, it's inverse, it's additive inverse. Additive inverse. Yeah, it needs a multiplicative inverse too. It needs a lot of stuff. What's the smallest subfield of what's the smallest subfield of C that contains 2? That sounds stupid. 2, 1/2, 2 plus 2, 2 plus 2 plus 2. All the even numbers. So put a lot of things in there, right? Okay, I don't have a good idea of what that field looks like, but that's okay. Consider the group field automorphisms of F. Oh gosh, okay. So an automorphism is an isomorphism from something to itself. We had isomorphisms yesterday. These are field isomorphisms, so they're going to preserve addition and multiplication in the field. Right, so elements of G permute the alpha I. Why does an alpha I have to get sent to an alpha I, not, for example, 2? Why does alpha 1 get sent to alpha k, not to alpha k? Okay, we'll get there. And if an element of G fixes all the roots, then it must be the identity. Okay, fine. Thus, there is a natural injection I from G to the permutation group with n things. So Sn is the permutation group where you have n objects and you shuffle them. S for shuffle, S for symmetry. Rearrange them such that alpha I of G of I. What on earth is going on there? So take your element G, and the injection says inject it from G to symmetries, and then read I. That first one is a kind of iota for the injection, and then that one is the letter I for the index in 1 to n. Oh, it's bold using iota and I. Anyway, iota of G, give me your permutation corresponding to G of I, which permutes. Okay, so that's the. Okay, for each field automorphism, they permute the AI. So you can define a kind of symmetry in Sn, a kind of permutation, based on looking at what the field automorphism does, such that, oh gosh, down here, it's something to do with the way the alphas get mixed around. For each I want you to look at where G takes AI, What is this? G of AI. Yeah, so G does mix around the AIs, but it gives back. Doesn't that return a? Doesn't return a different AI in the subscript down here? Something like this, right? You want something like this. Okay. Okay. There's a permutation defined by the way that G mixes up the alphas. And because G is going to be a subset of Sn, it's finite. So here's a finite group associated with that original polynomial based on kind of permuting the roots. I need to know much more about field automorphisms, I think. The person writing these notes says I just exercise or by construction, and these are things that for me require more explanation or proof. Well, work. I suppose exercise means that I have to do the work. Okay. Fundamental insight of Galois was that the group theoretic properties of G provide crucial information on P. The structure of G alone determines whether it's possible to express the roots of P from its coefficients using a closed formula containing only polynomial expressions and extractions of kth roots. That's the thing we're looking for. Solvable by radicals. Able to answer in the negative. So no, not quintics. Are there polynomials which are not solvable by radicals? Answer's no. And then there's Bruder compass constructions, trisecting arbitrary angles. Fine, okay. Grothendieck says it's faithfully flat descent. Okay, I expect the reader to be familiar with the Part A course Rings and Modules. I skimmed it yesterday. If you didn't attend the course, I skimmed it. Studying the material alongside. Okay, fine. Flip between them. I skimmed it. Well, okay, I should be wrong. A is defined by B, such that if and only if equivalent to. Okay, we've got some notation. GH for the question group. We had that yesterday. I mean for rings, but same notation for groups. And then what's this spot's doing? Spot is taking G to. Wait, so does that mean I'll have to see an example of that? I think, but does that mean we're going to be writing G spots or G spot? It's a unary operator, so I don't really know where to put the spot. Or maybe square brackets. Oh, we're going to make maybe it's the square brackets like that for the quotient map. Maybe that's what we mean. Right, square brackets around and put an H. Okay. Here's an injective map. I like this symbol. I haven't seen it before actually. Oh, it's on the previous page. But what is that? S goes from T is an injective map. Just quickly remember what injective means. Ah, yes, different things go to different images. Okay, I like that a lot. Okay, no notes so far on the build-up. The material in this section was already covered in the Rings and Modules course, i.e. yesterday. Let's have a look. Here's a ring. There's a quadruple. Fine. R plus dot multiplication 1, 0, quintuple. Anyway, never mind. I'm changing it on my copy. Quintuple. R is a set, 0, 1 elements for R, plus and dot. Now we're going to insist that 1's not 0, probably. These are the rules we had yesterday. We're insisting that rings have identity. So we need to remember that. Oh gosh. There was something about ideals, not necessarily, some sort of, not necessarily being rings. Goodness. Yeah, there was something yesterday about if texts insist that rings have identity. I think maybe that's what unitary means. Not sure. Then there's one caveat later on in those rings notes, which I assume this person making these notes knows as well, right? So I don't maybe have to track it. Ring homomorphisms preserve multiplication and addition. Obvious notion. Okay, fine. There's a subset that's a ring. Brilliant. In this course, all rings will be commutative. Brilliant. Ring will be a commutative ring from now. So when we say ring, okay, good. Okay, rings, domains, what have we got? We're going to call it R. We're going to use this infix notation for the multiplication. When we want to insist on the fact one put the subscript R on, we saw that yesterday. Inverses, units, integral domain if you can't multiply to get 0 for non-zero elements. Irreducible if you can't reduce it into two other elements. Z and Z are integral domains. That's C of X, complex polynomials. Fine, okay. Subset's called an ideal, it was an additive proof, and for all A and R and B and I, multiplication under anything in R with A times B is in I. Okay. Is an ideal. Okay. So this is making maybe a tiny distinction that I glossed over yesterday. The definition of ideal, it seems to be separated from the idea of ideal generated by H. Is every ideal generated by a subset? Yes, every ideal is generated at least by the subset of precisely all of its elements. Take all of its elements, and an ideal also is closed under addition and linear combinations, so this finite R combinations will be in the ideal, and nothing else is. Good, okay, so no distinction needed. Okay, form like that. Okay, so we're using round brackets for our ideals today. Make a note of that. Yep. Yeah, okay. I'm going to write R line T. Oh, good, that is the right way around, isn't it? That means that there exists some element of R in the ring, some element of the ring, such that you can multiply R by that to get T. So this is division-y stuff. Good, okay. This lines up with what I think about division of numbers and sensible ideal stuff. Kernel of F, any ideal is Z is principal, because Z is on my chart somewhere. Quick look at the chart, got to revise the chart. Any Z is a Euclidean domain, which means it's a principal ideal domain, which means that the ideals are all principal. Things go from right to left on that chart. Things in the bottom row says what things imply other things. That's notes from yesterday. So down here, any ideal of Z is principal. Okay, can skim this bit, I think. Nope, we're still going. This is the idea of quotienting. Equivalence classes look like that. There's a natural map, standing R to its equivalence class. Right, and we are doing this square bracket subscript I. So this is the equivalence class, which was, it's going to be written like this in Galois theory notes. And I think we were writing it R bar yesterday in rings. When I say in Galois theory, I mean in these Galois theory notes. Okay, I'm sure other people do other things, but I'm just making notes so I remember, try and explicitly form the memory that that's the notation change that we were making between yesterday and today. Okay, unique map F prime goes from, yep, this is the isomorphism thing, good. Yeah, okay, good. Prime if, oh, okay, ideals are simply prime. This person is defining, this is Damien. Damien's defining a ring to be prime if that thing's a domain, and maximal if that's a field, which is sort of the other way round to how we define them in rings. Fine, okay. We showed they were equivalent in rings. Unique ring map, yep, which gives you the characteristic, which we had yesterday. If there's a domain, are we calling domains? Quick check. Yeah, okay. So we're calling domain. So ID in rings yesterday is going to be a domain today. Just domain, just D. And I missed this bit about the set of units, but it's the same as what we had yesterday. Okay. So there's three things up here: integral, or a domain, or an integral domain. Yesterday we said integral domain a lot. The challenge of piecing together different books or references or notes, or if you find something on Wikipedia and find it on Wolfram Mathworld or something, matching together the notation is an important step, I guess. I'm going to be doing quite a bit of it this morning. Okay. Ring structure on R. Okay, give it the obvious ring structure, or apparently the good, unique ring structure. Okay, if R is a domain, which means integral domain, here's fields. 1's not 0, and you can invert everything. Yep, sure, okay. Multiplication is, with respect to multiplication now, it's a group. There is a field and an injective ring map from R to F, such that if phi1 goes from R to F1, okay, let's read this. There is a field F and an injective ring map. You can map from your ring to F such that if you map into any field F1, there is a unique ring map, lambda, which goes from F to F1. Oh my goodness. R to F with phi1 to F1, and there's a unique ring map, lambda, F to F1, such that phi1 equals do phi and then lambda. Okay, sort of two ways around this triangle. Oh my goodness, this is the field of fractions. It's quite a... Not the definition of fractions that we saw in rings, because it's not defining any fractions. Map from the domain to the field. What is this trying to say? This is sort of, oh, okay. I was going to say that this is uniquely determined. That seems to be the point. You get from your ring to the field. Oh, we did see how to do this, right? It was like adding phi of m over n. Oh, no, so you build it like this, don't you? No, injective ring map. From the ring to the field. Do I need to look back at those notes? What did we do? We had something for... I'm thinking about trying to build those fractions where we had phi of m. Oh, this thing about... So you've got your fields, and you've got sort of like phi of 1 plus 1 plus 1, like m times, and you have something like phi of 1 plus 1 plus 1 n times, and that's phi of m, and that's phi of n. Is this helpful? Not really. I was going to say then you divide them, because everything's got inverses, and pure mapping between fields. And if everything's respected, then you end up with something unique. No, maybe not. Okay. I know what the field of fractions is from yesterday. I don't quite understand what this is trying to do. Anyway, exclamation mark to come back to this. Let's not prove it. Lemma 2.2. Doing a bit of revision. Weird place to be. Oh, end of lecture 1, here we go. Oh, we're in half an hour, that'll be good. Speed running. There's now a speed running stream. KB field and ideal. Fields only have boring ideals, that's one of the notes from yesterday. K and LB fields, and phi from K to LB a ring map, then phi is injective. Okay, fine, okay. Field to field maps are injective? Because if two things went to the same place, think about the ratio. No, look at the proof. Consider the kernel. Kernel is an ideal of the field, right? Fine, okay. Rubbish. Well, not rubbish, but the consequence of the fact that fields have boring ideals. Okay. half an hour end of lecture 1. Good stuff. Keep that up and we'll be home and dry by Christmas, I was going to say, but that's ages away. Rings of polynomials, my favourite. Okay, you build them up one variable at a time. Here's the polynomial. P is mnemonic if the first thing is 1. Okay, rings have 1s, fine. In this world. The natural number degree of P is the degree. Right, yeah, okay. Add up D, this thing here. That's D, highest power. Element of T is a root of P if you can plug it in and get 0. The degree of the 0 polynomial is going to be called minus infinity. And then we have, if R is an ID, so is R of X. Do we have that on the table? Let's double check if that's on the table. Yeah, there it is. If R is an ID, if R is an ID, Rx is an ID. In the table right there. Good. Down. Okay. There's a proof which we're skipping. The proof is look at the highest coefficient. Good. If K is a field, which write Kx. Oh, right, okay, for the field of fractions. That's what I thought we were doing for ideals. Oh, does that make me reassess what the... Oh, the thing in the preamble was using round brackets, not square brackets. Hang on. Yeah, okay. I'm going to write this nice and large. Maybe I'll put it on my notes page. Yeah, notes page. So, K field. K with square brackets is polynomial ring. K with round brackets, field of fractions for that polynomial ring. Field of fractions for a polynomial ring involves polynomial denominators? Sounds weird. I'm going to write it down anyway. Okay, over here then, we're going to have some Galois theory notes. So this is notation. Okay, xy for polynomials. Okay, round brackets for the field of fractions of that thing. And I've written out with 2 variables. I know in my heart that it applies to more than 2 variables, but we'll leave that be. Good, okay. I think really I should at some point go and understand what the field of fractions for a polynomial ring is. Is it just rational functions? I don't really see why they're going to be relevant, but hey. I don't know anything about what's going to be relevant, I suppose. Okay, Euclidean division. Case of field. There are 2 polynomials. Oh yeah, okay, so this is Kx. If K is a field, then K. How am I going to pronounce these? Polynomials in K form Euclidean domain with norm degree of the polynomial. Okay, yeah, there we go. Okay, notation. Okay, and then Kx is also a principal ideal domain. We're going right to left on my diagram in that table. All those ideals are principal. K is a field, and if this I is in Kx is ideal, polynomial, minimum thing is a generator, use Euclidean division. I like how that's just a really accelerated version of a proof that we saw yesterday. We're not supposed to be reading proofs today. Where does the proof stop? Note that if R is a domain, and I think this is new. No, this is carrying on. Okay, new bit here. Unique factorization domain is domain R, such that you can build things out of irreducibles and uniquely. Good, okay, PIDs are UFDs, which is why UFDs are to the left on my table. Proof in rings and modules. Okay, now these notes are quite heavy, I think, on using numbered references. Sequence of irreducible monic polynomials. Yeah, you can factorize F. Unique up to permutation. Okay. It's something that you kind of take for granted in school, I think, that you can factorize polynomials kind of uniquely. GCD. Okay, because this is a principal ideal domain for the unique monic generator of the ideal generated by those elements. Greatest common divisor, which I think is the same idea as highest common factor. Unique monic generator. The highest common factor is only unique up to units, so this is a bit more insistent that this is monic. Totally missed with that arrowhead. There we go. Better. Suppose that R is UFD. Element F is irreducible if and only if F is prime ideal. Is it UFD? Oh, quite left on the chart. Don't remember this. Irreducible elements form prime ideals. Oh, what do we know about UFDs? Table. Oops. UFDs. Oh, irreducible elements are prime. And then prime. No, that's not quite the same as what's being claimed here, is it? Well, maybe we need a note. It's a good fact about UFDs down here. A non-zero element is irreducible if and only if F is a prime ideal, which means that our quotient I is an integral domain, right? Yeah, okay. I want to write this down. I think irreducible elements give prime ideals or something. Irreducible elements. F. Oh, is this just in polynomial rings? Hang on. What's F? Why are we using F? What's going on? No. There's no polynomial stuff going on here. Back in. So irreducible elements give prime ideals. Right, what have we got? Okay. So 2.8, R is a PID. Let I be a prime ideal and suppose a non-zero prime ideal, then I is a maximal ideal. Oh, is this like the link between primes and irreducibles again? Okay, I kind of want this too. Anyway, good. Okay. So your prime ideals are maximal. So I go from an ID to a field. Yeah. Okay. I can believe it. I'm trying not to read the proof. I'll be a principal ideal domain. I'm just trying to remember if we had it yesterday. I've got the sun in my eyes. So I muted myself and then said 2 seconds. So that's not how this works at all. Okay, I think I want this as a note. PID. Maximal prime ideals are maximal in a PID. Where are we over here? Prime ideals are maximal. It goes there. That's really terrible handwriting. Let's have one more go. Oh no, I lost my lines. Good. What next? The KP field, it's FB in polynomials generated with K coefficients. A, B, a number of the field, and A is a root if and only if the factor theorem. we saw that yesterday. There is a polynomial in there which has no roots. And a decomposition like this. So you pull out all the roots one at a time. Man, proof is clear apparently. Here's the Eisenstein criterion from yesterday. And if f is prime, let P be a prime. Suppose that f mod P is irreducible, and f is irreducible in Z. Oh, we had this yesterday as well. FP is what we're calling. I think yesterday we would have called this ZP, like that. Today we seem to be calling it this, which is the same thing because there's a, I guess, isomorphic, if you like, kernel of the map. So you take the map, which is x goes to x mod p. The kernel is p times the integers. The image is isomorphic to. Image is kind of ZP, sort of. Yeah, you take it to its contrastive class. It's the map. Square brackets with it. Square bracket subscript kernel. Okay. F mod p refers to the polynomial. Okay. Yeah, reducing all the coefficients. That makes sense. So if you could, the idea is that if you could genuinely reduce it, then you can also reduce it mod p. Just write out your reduced version of mod p everything. I think. Okay. Gauss lemma. This was so good yesterday. I didn't really grasp it, I think. It just seems important. F is monic polynomial in Z of x. F's irreducible if and only if f is irreducible in Q. Content function. R and Q star, which is here, I think. The units of Q are everything except 0, so this just means non-zero rational number. Take some prime numbers. Then the order is order P of R. Oh, this is new. As the order of. I wonder how much this is going to come up, but sort of want this. So R is, what are we going to write? If R is P1 to the M1, Pk to the Mk, order subscript P of the number R is the order of the power of that prime in the number R. Order, oh, this is also notation, so I'm going to put it over here. Order PR is, I'm going to write it as K such that P to the K divides R, P to the K plus 1 does not divide R. That's a kind of alternative way of saying it, I think. Yeah. We're in the rationals, what could possibly go wrong? Wait, hang on. Oh no, we're in the rationals. What could possibly go wrong? Things don't really divide each other, do they? Because we've got rationals. Oh, what are these then? These could be negative numbers. Right, okay, look. If they're negative, then not really correct to say things divide things. For R and Q, R equals P1 to the M1, P2 to the M2, PK to the MK, PK, P, what do I want here? The ith prime is Mi, the power of that prime. Okay, I now think my way of writing it is worse, but hey, at least I wrote it in my own words. Right, so the content is P to the power of R is product over all primes, P to the minimum of the order of, I guess, C. Oh, of the coefficients. Oh, yeah, this is the thing we had, right? Primes that divide all the things. Oh, we have rationals in there. Yesterday for integers, I think. Today for rationals. Clearly we have got to P and Z if P and Z. Oh, right, okay. If and only if. Because if just one coefficient was not an integer, then it would have some denominator. The denominator would put some negative power on a prime for r, where r is that coefficient, and then the minimum would be negative. So a prime would be raised to a negative power in here, and the content wouldn't be an integer. Okay. Lemma. If P and Q are in, if P and Q are polynomials with rational coefficients, then the content is multiplicative. Oh, that is good. And it's to do with pulling up factors and then multiplying primitive polynomials together. For primitive polynomials, it all worked. We did see that yesterday. I don't think I really grasped it, but technically it's a thing we've seen. Okay. Proof of lemma 212, which uses 213. Gauss lemma using this like lemma due to Gauss. Okay, fine. Wait, is that really what it says? Lemma 2.12, Gauss lemma uses lemma 2.13, Gauss. So this lemma is the Gauss lemma. This lemma is Gauss. I mean, the second one's just being attributed to Gauss, I guess. Right, time for some actions of groups on rings. So this is moving slightly out of what we were doing yesterday. Have a quick look at the menu at the front. So in here we had that smiley face so far. We're about to move into 3 or 4 pages of actions of groups on rings, which we're going to do now. Can I click that? Is that a link? Yes, it is. Oh, brilliant. I think PDFs might be underrated. So that's sort of hot take. PDFs are not very good. They're definitely overrated. Right. Okay. Awesome. We got some slightly scary notation here. And we got words with subscripts for other words. But this is going to be fine, I think. It's a group of bijective maps. That's important. Let's underline the important word. S to S. So they give to themselves either automorphisms. They ought. The group law is given by composition of maps. Okay, so you've got different ways of mixing up the elements, and you want to mix them up like that. Okay. Whoa, the quest for the Quintic is involving a lot of group theory this morning. We're going to get to the Quintic. We're going to see the Quintic today. But to get there, I've got to go through, oh my goodness, group actions again. And it's been more than 10 years since I knew what a group action really was. Here we go. An action of G on S is a group homomorphism. Oh my goodness. Okay. From the group you showed me, the start one, to this slightly horrible notation for the group of different ways to permute the set. Is that just, are the set automorphisms just the symmetry group? Maybe? Group law is given by composition of maps. Yeah, so I guess if it's an infinite set, then what are you going to do? But I'm going to imagine a finite set. So automorphism as a set of S is just a permutation. And then what I've got is an action says, show me your group, and that specifies a way to stir up the elements of S. Okay. Gamma is in G and S is in S. We write. So the group effect on a member of S. So if you want to imagine that the group is just doing something to the set rather than in here, is to first look up which permutation it refers to and then apply that permutation to S. So strictly the group gets mapped to a permutation. You can imagine that permutation applying to some element S. Also sometimes write gamma S. Morning Ashwindar, 10101. This is a maths live stream. Welcome to chat. We're going to write S to the G. I'm trying to learn group theory. No clue what's going on because sound is off. I'm going to type in chat. There we go. S the G for the set of invariants of S under the action of G, i.e. those elements which gamma sends that element to itself for all members of the group G. Yeah, okay. So you've got a group, you've got, let's draw like a set. I always draw little circles for everything. You've got a set that sends each thing to one place. Each thing to one place, so it sort of stirs the elements around, maybe like this. And some elements stay the same. And so for this element gamma, this is the stirring that I'm doing on my set S. This is the stirring that I'm doing on my set S. So sometimes that leaves elements fixed. Invariants of S are the action of G. So for all G, so elements that never move. So never move. Okay, I want some of this notation down, I think. Oh, we're going to do orbit stabilizer stuff. Good. Gamma S is the orbit when you look at everywhere you could go onto G, which includes the kind of connected component under all possible sorts of stirring. It tends to form these like complete graphs because of group theory rules. This is good stuff. We should learn this at some point. This is revision, I suppose, for something I learned about 10 years ago and have touched on briefly since then, but never really. Okay, so if S is in S, we let this be the orbit of places you can go, and the stabilizer is going to be those elements in G which fix those particular elements of G which fix a particular element S. So things which fix. If the G is clear, okay. Suppose that S equals R, where R is a ring. Okay, so now we're not just permuting a set around, we're permuting a ring. Yeah, my ring really could be infinitely large, so probably best not to think about symmetry group, right? Sn, which is what I was previously imagining. I drew a finite set there. Compatible with the ring structure. Compatible with the ring structure, or the G acts on the ring, if the image of phi, so the things, the permutations that you're doing, that G accesses, the permutations that are brought to you by G, lies in the subgroup automorphism of rings, the group of biadjective matches with respect to the ring structure. Oh my goodness. So we say the action is compatible with the ring structure if it's one of these ones which respect the ring structure. Okay. I want some of this notation on my notes page, I think. I want to get that alt sets thing down. Alt sets G? Or is it alt sets of S? What are we using? S, I think. G is going to give me some way that a group looks at the action of this. Automorphism of S as a set. And then aut rings S is automorphisms of R of S as a ring respecting ring stuff structure. Okay, and then I want this notation of SG for the invariance of S onto the action of G. Action, let's get action down. Action of G is phi G to ought. Let's put rings because I want to only think about those ones today. And then okay, SG invariance of S under G, orb GR, stabilizer GR, to be the orbit of R in S under G, and that's the stabilizer. And I think I remember enough, having seen them, what those things look like, where you go, and what keeps you still. Okay. Feeling good. This is complicated stuff, but gotta learn it somehow, right? Okay. The things, if RG is a subring of R, invariants are a subring. Wait, hang on. So the thing's fixed by all elements. If you're fixed, then that's a subring. It just sort of respects the if it's fixed, then and you do a linear combination, then fine, that's also fixed. I think. Yeah, it's the proof down here, isn't it? Yeah, it's just sort of fine. It respects addition and multiplication. So if things are fixed, then the sum is fixed. Oh, I like that gamma can give us back, because it's an automorphism. It can simplify. You can remove things. Sort of, maybe that's obvious. Gamma of A can just be A. It doesn't live in a separate space. We had a lot of stuff with ring homomorphisms where we were worried about bars and things yesterday, and how the set we were mapping to is very different from the set we were mapping from, so we have to be careful about the distinction. If you've got an automorphism, then the thing that's nice is that gamma of A could just be A, so you might get to be able to just simplify gamma A to be A. Automorphisms. It's a very strange live stream. It's a very, very odd live stream. Okay. And if R is a field, then the invariance there in a field, because you can also respect. Oh, do you respect multiplication? Oh yeah, because you respect the ring structure, which includes respecting multiplication. If the inverse exists, then you're going to end up respecting it. Okay. I don't really know why we care about RG though, right? Stabilizer, the things that are invariant. Oh, I suppose it's got nice properties. Look, could be a subring, it could be a field. There's a natural action of Sn on the ring. Oh, here we go. Okay. Natural action on the ring. Now with square brackets, that's the polynomials. So here we go. And it's going to switch around the variables. Symmetric polynomial with coefficients in R is an element of. It's fixed by any permutation. So any way of switching around. Right. Any way of switching around the variables gives you the same polynomial. So like. XY in R of X and Y, because if I swap the variables, I get back YX, which is the same thing as XY. Okay, symmetric polynomial with coefficients in R. Right, okay. Oh, what's this example? So I wrote an example down on the right, and now I notice there's a big example here. What is this? Sum over increasing i's. I want to do the product from j is 1 to k of all of those. So you've got increasing xi's. If you're going to sum, oh my goodness. So if k is 1, then it says take one variable and do some addition. If k is 2, it says first do products. Multiply them. Oh, it's gone dark. It's gone dark because it's chucking it down. It's really raining. Britain. This live stream brought to you by English weather. Oh, it's actually amazing. Right, well, good. Okay. Sn. I've seen these before. These are good in. These are important in polynomials. Yes, here they are. Sorry. Always read the next line before I do my incredible insight. I should always read the next line down. Fundamental theorem of the theory of symmetric functions. Oh my goodness. That's very tidy. That's very tidy. Oh, that's very tidy. Oh, let's write that down. That's going on the quest log. You can't see my document names, but the one with like the map and all the kind of summary notes. So this is a notation page, and this is going to be over here, a page that goes R of just facts that we've learned. And I probably should put in notation what the S means, but let's just have that back again. Over here, have I written it down correctly? Yes, I have. Do I want to write down this SK? No, I'm going to write down S1 and S2 and then put a dot dot dot. Symmetric polynomials over here. Plus dot 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 plus xn. S2 is equal to x1, x2 plus x1, x3 plus dot 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 dot, comma dot dot dot. You know, add together products of some of them. Don't repeat yourself. Groovy. Where have we got to? Down here somewhere. It's a fundamental theorem of this theory of symmetric functions. So on the right, that's the polynomial ring of building polynomials out of these symmetric functions. It's like you've got the one where you add all the variables together and maybe you square it, multiply by 3 and add this one. So it's kind of obvious those ones are symmetric. They're definitely in the stabilizer on the left hand side. Anything like that? Challenging. So the theorem, the proof, more precise formulation. Oh, right. Sends, okay. Oh my goodness, the ring is the image. Yeah, okay, hang on. Precise formulation, always exciting. Map of rings, which sends xk to sk. Oh gosh, okay. So up here it's presented as going from a ring to ring with x's, but we're imagining replacing xa with our definition of sk above, and which sends constant polynomials to themselves. Fine, okay. You've got to do something with them. The ring like that, or stabilizer, sorry, no, invariance of that ring is the image of phi. Again, I can sort of see why I understand that the image is, why that thing is in the image, but not kind of obvious it's in the image. Anyway, oh, and the proof's going to define lexicographic ordering on monomials. Crikey. Transpositions, loads of group stuff. Gosh. Repeat this for other, oh my goodness. All the monomials in this polynomial, strictly smaller, oh my goodness. Keep going. Oh, right, okay, so it's a crazy method to express something symmetric in terms of SNs, SKs. Oh, I don't like that. Yeah, that looks really difficult. Let's not read that proof now. Example. Oh, this is the thing you do at school, isn't it? Huh. Write the sum of the squares of the variables in terms of the coefficients. This is very relevant for solving polynomials, isn't it? You can always do something like that. Oh, and I think I've done exercises like this, where you're trying to get from squares or cubes of the roots in terms of the coefficients. So you've got to. So this one's how you get to squares. You could do cubes instead. Cubes will be Right, it's symmetric. It is symmetric, but can you write it in terms of the symmetric polynomials? That's the challenge. And you kind of do it, not inductively, but you do it step by step, starting with the highest powers or something of the highest monomials. It could be really complicated because you could have lots of weird stuff. You've got to do term by term across your general polynomial in this ring down here on the left. This ring's got a lot of things in it, but not that many. If you can do it for monomials, they're a basis for everything. Okay, that's what we're trying to do. Right, okay, so skipping the proof for now, symmetric functions build those simple symmetric functions build anything that's kind of symmetric under permutations. It seems quite good. It tells you that if the thing you're trying to calculate looks symmetric in the roots, is it fair to call it roots? Not really. It reminds me of roots, but it's not quite roots. If it's symmetric in that, then you can rewrite it in terms of those basic combinations. So yeah, okay. These things on the left have no powers of s of the x's. So you want to write x squared or something, then you x squared plus y squared plus z squared. Then you're going to have to do some rearranging. So that's kind of what's going on in here. I think I'm trying not to get distracted by the details of the proof, just work out what we're doing. And I remember I've been saved by this example, which reminds me of doing school maths, things I did at school. Fine, okay. It's funny that I remember high school better than I remember some of the university maths I did. Okay. I guess in high school we spent a lot of time rehearsing and practicing and doing things again and again and again. I'm saying high school for any American audience who have joined in. I figure we're on American time right now. Oh no, we're definitely not. I've remembered how clocks work. Right, good. Okay. I should be on like a... Where are we? Who knows? Okay, we got some new notation down here. Ooh, there's a squares thing going on. What is that? So this is in the invariant set. It's an integer polynomial. It's fixed by every sort of symmetric permutation, because whenever you come along, if you try switching these, who cares? It's going to fix the square. You could write this in terms of s's if you wanted to up there. And this one is fixed by all the even permutations. A is the subset of S that contains the even permutations. It contains half of them. Even permutations are ones that you make out of an even number of swaps. So, for example, if you've got 3 elements and you permute them around like that, you can build that out of swaps by saying step 1, swap those 2, step 2, swap those 2. That's 2 swaps, so that's an even permutation. It's kind of weird that there are other ways to build it, but it's always preserved. It's like a kind of parity thing. It's pretty good. Sign of permutation. Right. This is... Yeah, okay. This is the alternating group. The definition's on the screen. That's like the 10th time that I've tried to explain something to chat and then realised it's on the screen as well, further down the page. Fun times. If sigma is in this, then delta is equal to... when you do a permutation, you either get plus or minus 1. So it might not be fixed. It either goes to this or it goes to the opposite of this. Because you might bring in there an extra sign change if you flipped an odd number of these things. Each one's got a minus sign. So if you do these switches, then odd number of switches will flip an odd number of minus signs around. That's what's going on here. Sign of the permutation is itself a group homomorphism. If you think about this as a multiplicative group structure, fine, okay. Sure, yeah, okay. First course on group theory. Which I've done, but I'm not sure Twitch has done. So this feels a little bit unfair that I can just go, yeah, I understand that, and not explain it to chat. Sorry, chat. It's a study with me kind of stream. Okay, so I want capital delta for product of all the difference of squares. Getting a lot of notation today. So this is the product for I less than j of xi minus xj squared and little delta of x1 up to xn is the product of I less than j xi minus xj not squared. I think I've got that right. Let's quickly look back over here. The thing I'm trying to do is focus on getting through the statements in the course rather than reading all the proofs. I'm just trying to understand what they say. Yeah, I less than j, less than n, I suppose. Okay. Alternating group. It's funny that it's called the alternating group, even though it's kind of the ones that don't alternate. The permutations, as you do the transposition permutations, alternate between odd permutation and even permutations. So it's kind of weird that we call just the even permutations alternating. It's like if we called the even numbers the alternating numbers. It's like, well, it's kind of not the even numbers that alternate. It's the pair of them together, right? That alternate. Or sorry, I just did this kind of interleaving fingers thing, but I did it really quickly and it looks really weird. So I'll do that slower, so you can see 100 even and odd numbers. Good. Looked like a sort of weird coral reef growing at the bottom. Good. Ashwind's here again. Good to see you. You got sound on? Maybe not. Oh, that's called the discriminant. Hang on, let's get that in. Down here, polynomial is called the discriminant. That's the capital delta one. So make a note. Discriminant. Okay. How are we doing? Been live for an hour and 10. We've got some. This is the fundamental theorem. Fundamental theorem. What do we call this? The fundamental theorem of the symmetric function, I think. That's what this was called when we saw it over here. Of the theory of symmetric functions. I can't just put fundamental theory of symmetric functions. I'll work it out. Good, okay. Right, okay, so we've got the fundamental theory of symmetric functions. We're 1 hour in, and we got this. We skipped a proof, but we've got this definition of discriminant here. Does it line up with other things I know about discriminant? Not really, right? Has it got anything to do with b squared minus 4ac? Not that I can see immediately. B squared minus 4ac. That's got some squaring in. That's not nothing. But this is like about polynomials in more than one variable, so I shouldn't be thinking about b squared minus 4ac anyway. Okay. Proof. Yeah, good. Okay. SN's product transpositions. Yeah, okay. End of lecture 2. Okay, we've skimmed through 2 Galois theory lectures in an hour and a quarter. I noticed that the first one took half an hour, the second one took 45 minutes, and we skipped more proofs than the second one. So, I fear the second one may have been about half the speed of the first one. May have discovered a geometry series. Okay, let's go. Welcome to the maths live stream if you've just joined us. I'm on a quest for a Quintic. These lecture notes contain a description of why Quintics don't have a general formula. I would like to understand them. Unfortunately, reading maths is really difficult. So if you're joining me on this quest, we're going to find out what's going on. We're about to revise field extensions. When I say revise, I mean we skim read them yesterday, and now I'm going to skim read them again. Let's go. Okay, field extension of K, or a K extension, is an injection. We didn't call them K extensions yesterday, but maybe we'll call them today. It endows M with the structure of a K vector space. So K, there's a copy of K in M, and they're both fields, which is what we had before. Mostly going to use the notation MK. Okay, I need to write that down. What did we say yesterday? I think we had the colon stuff yesterday, didn't we? So yesterday was all about colons. Today we're going to write MK field extension of M over K. Oh, that's how I'm going to refer to it. Okay, and back yesterday, yeah, we were calling it with a colon instead of a vertical line. Okay. So today, we've got this. Good. Okay. What are we doing? We would like to understand these. A map from the K extension M over K. How am I going to pronounce this? I'm going to say M over K. It gives me a word to pronounce in the middle, and it makes it clear to me that M is larger than K. I've got to remember it's that way round. Very, very basic understanding today. Try and remember which way round things are. Okay. A map from the K extension to a different K extension is a ring map, which is an injective compatible with the injections K goes to M and K goes to M prime. Oh goodness. Yeah, all these maps should just respect everything, right? Okay. And now this looks important because we're getting onto automorphisms of a field, which was mentioned in the preamble. Automorphism KM for the group of bijective maps of K extensions from M to M. Okay, so if you've got your large field M, you can do an automorphism, and we're writing subscript K there to remind ourselves that we want automorphisms of M that respect the kind of K structure. We've previously seen sets and rings as the subset. Now we're writing K for the specific field that we're respecting. Bijective maps of K extensions from M to M that preserve them. It's the subgroup of automorphisms of rings which are compatible with the K extension structure of M. Goodness me. Which reminds me of, like, in the complex numbers, this is like taking your complex numbers and replacing, I think, what can you do? You probably still just send 1 to 1. You set I to minus I, complex conjugation. Might just be, there might be it. Any map of K extensions from M to M is a bijection by rank nullity. Oh goodness. So rank nullity is this thing about maps of vector spaces, right? About the rank of the map and the things in the kernel, dimensions add up. Let's think about the assumption of bijectivity was redundant in the definition. Goodness me. Okay. I can sort of see, I don't know about rank nullity for infinite dimensional vector spaces actually. Not really sure what rank nullity would say for infinite dimensional vector spaces. I'm lost. Hooray. We're on the quest and we're lost. Standard procedure. Any map of K extension from M to M is a bijection. K extensions. M to M is a bijection. Oh, because we've got a field here, haven't we? We've got a field, so if you map two things to the same place and you're respecting multiplication, then I could look at where would you send A, B inverse? You would send it to image inverse, which would be identity. Yeah, I guess it's, where would you send A minus B? Oh, linear algebra time. Yeah, where would you send A minus B? You would send it to image minus the image would be 0. So just take the stuff that you're sending to 0. And if you're sending anything non-trivial to 0, then now I can ask, where are you sending the rest of the stuff, right? Because you should preserve. Yeah, okay, rank nullity says you're sending some stuff to 0 and other stuff is in your part of your rank. I don't see how this can make it bijective, right? Okay, something to no understand here. We should say the field extension is finite if the dimension is less than infinity. Fine, okay. Which I hope they are. And talk about the degree. There's the Tower law again, which we saw yesterday in rings and modules. Yeah, you can make a new basis by looking at the kind of products of those things. Right, N is going to be the annihilator down here. Those polynomials in Kx such that Pa is 0. Those things such that for A and M, the big set, it's an ideal of K, brackets easy. Sure, because if you multiply anything else, then you're multiplying Pa by 0, so you're going to be fine. A is transcendental. Oh, we had these yesterday. I'm going to put annihilator on my notation sheet. Those polynomials such that P of A is 0. It's the annihilator of A. No subscripts or anything on the left. This notation page is getting quite long. Those polynomials P of X in K of X such that P of A is equal to 0. So example that I've got in mind, in the complex numbers, the annihilator of I is things like x squared plus 1, because in that world, I've lost connection to my notes. That's a thing that can happen on live streams. In complex numbers, x squared plus 1 is the thing that, yeah, so we're going to have a definition of minimal polynomial coming up, I think, and whether things are transcendental or algebraic. There we go. Notes have reconnected. Oh, the internet. What is the internet like? These notes are being beamed from a small tablet onto a larger machine that's sending them across the internet. Just standard internet stuff. So if there's nothing in Kx, oh, see, these are in the smaller one. Yeah, okay, so for A and M, so I do need some notes on my annihilator thing over here for A in M, M over K. I'm liking the word over. I don't know if it's used by anybody else or if it's technical, but I'm going to keep saying over for these field extensions. M over K. M over K. Complex numbers over the reals. Because I kind of live above, right, and around. Might hurt me later on. It's not a great mental model, I think, but hey. Having these kind of mental models of where stuff is helpful to me anyway. Algebraic if there aren't any if there aren't really any polynomials that do that, then we say it's transcendental, like how square root of 2 is transcendental over the rationals. Is that true? No, that's nonsense, because there is a polynomial. So that pi is transcendental over the rationals, because there's no polynomial that pi satisfies. That's kind of what this notation is trying to do, I think. So you can have numbers. So can I think of a field extension that actually does this? No, not immediately, because the ones I'm imagining are usually generated by adding in roots of polynomials, so that you explicitly have a polynomial in the annihilator. The whole point of going to my field extension was to gain a root of this polynomial. What do you mean, transcendental? Okay. So I guess the reals are a field extension over the rationals, where pi is transcendental. Okay. If A is algebraic, which I sort of hope it is for my sake, maybe I'm going to be surprised by this and it'll turn out that, oh yeah, is this going to correspond to this thing doesn't have a polynomial, doesn't have a root? It's kind of like, it's giving me vibes like doesn't have a root kind of thing. Okay, the Quintic is nearby. We're hunting this Quintic. Minimal polynomials, unique monopolynomial, which generates that, fine. Probably divides any polynomial coefficients k which are nulls. Yeah, fine, okay, that's what it means to be an ideal, I think. The ideal is prime, because, it feels like we should be technical here, right? Something about the structure of k of x polynomials. It's a unique factorization domain. That's not good enough. It's a Euclidean domain, so it's a principal ideal domain, so it's the ideal is prime. Oh, that's something clever. Let's go for it. No, but their reasoning here is there is an injection. And M's a domain. Yeah, fine, okay. M's a field, so it's definitely a domain. I suppose A is algebraic, then by lemma 2.7. This thing's irreducible. What was 2.7? Oh, 2.7 was a while ago. Oh, 2.7 was really a while ago. These lecture notes are quite keen on looking back. 2.7 was, if R is a UFD, then the irreducibles give prime ideals. And prime ideals are generated by irreducible elements. Right, back in again. Lots of learning this morning. Anyway, the irreducible supplies the monic irreducible polynomial, which annihilates A must be the minimal polynomial of A, also annihilator of A is the maximal ideal by lemma 2.8. Okay, there's some technical stuff flying around here, but it seems to be reinforcing ideas about minimal polynomial that I kind of wanted to be true, so I'm just going to accept it for now. First time through, we're going to try finding out what's in the notes, and then at some point building understanding by going back and looking at everything very carefully. Algebraic field extensions, if everything's algebraic, transcendental if it's not, fine, okay. Oh, and if it's finite, which is the ones I care about really, then it's algebraic, then there's an injection of k vector spaces. Since k vectors is infinite dimensional, that sounds like it. Is that accountability? I'm trying not to get too bogged down in proofs this morning. I feel like I have to defend that a lot. Nobody's called me out on it, but being a mathematician is often about understanding the proofs and asking loads of questions about why things are true. I want to get first an understanding of what things are out there. I'm going to keep defending it as practice. Right, separability, which is a new concept for this morning. Here we go. Okay, we've got k be a field, p in there, there's the polynomial. Define a derivative, right? Oh, and here the number d minus I, this is very technical, is understood as this added together d minus I times. Yesterday I think I went to town a bit on multiplication of some ring element by an integer, but that's how you define it. Good. Full analog of the operation derivation. Fine, okay. It's a k-linear map, and there's a Leibniz rule, which just always works. Well, that's nice. Okay. See the example sheet. Knowing multiple roots if... Oh, look, so this is the ideal generated by px and p prime x. So it's something to do with whether they have a common factor. Is the ideal generated by 1. Otherwise, we say that px has multiple roots. So common factors. If they have a common factor, note the following fact which justifies the terminology. If this then has multiple roots, then yeah, you can work it out that x minus rho I would be some sort of repeated root. It would appear in both, so it would be the highest common factor and generate that ideal. This thing's a Euclidean domain, so you could run Euclidean algorithm on it. Fine, try not to get bogged down in proofs. Keep repeating it so that I remember. 3.3 down there. Take a field extension, L over K. Show me these polynomials in K. which maybe we're trying to solve. Right, GCD, for the greatest common divisor, if you use polynomials with coefficients in L, the big one, then the normal GCD, that's equal to the normal GCD? Oh my goodness. Okay, fine. I'm just going to think about GCD being GCD. It seems to introduce something new and then insist that it's the same thing that I was expecting it to be. K is just in L, so this is fine, right? Yeah, Px does have coefficients in K. Euclidean division, but these things all exist in L, right? Find the generator. Coefficient in L, we get the same things. Okay, fine. I'm not sure about this. Algorithm, that's the Euclidean algorithm. Right, cool. Cool, moving on. Greatest common divisor exists or something, and it's nice. K be a field, L with K be a field extension. P of x has multiple roots as a polynomial of coefficients in K, if and only if it has multiple roots as a polynomial with coefficients in L. And this is to do with highest common factors between P and P prime, so it's like the same thing. Use the thing we were just talking about. Right, now suppose that Q divides P, suppose that P has no multiple roots, then Q has no multiple roots. These sort of things seem very reasonable. If I was doing a video for YouTube explaining this, I'd probably not mention this or prove it. I would just sort of take it as read, which is again not how maths works. But if you're trying to explain something, that's usually quite different from depending on who you're talking to, how much you explain it. Oh my goodness! Look, here comes the Leibniz rule. Yeah, okay, fine. This refers to this when I'm sort of just skimming through it the first time. This seems extremely reasonable that such a thing could be true. If P of x has got no multiple roots, and you look at a factor, then hey, shouldn't have any multiple roots, right? You sort of intuitively believe, but I would just multiply it up, right? Of course, we've defined multiple roots in this strange way involving P and P prime and greatest common divisors. So as a consequence, the proof is going to refer to those things. But this is just helping us check that it lines up with our intuition of what's going on there. 3.6. Take K of field and P in K, not the 0, 1. Suppose the characteristic of K. How much do I care about fields with characteristic that isn't infinity? Or 0, whatever we're calling it for the rationals. We're going to read it. No repeated roots. Oh no, this does look good actually. P is irreducible. If P is irreducible, then it satisfies this no multiple roots condition. Okay, fine. Can I quickly skim the proof to check that this actually makes sense for the case I care about, where the characteristic is, oh gosh, 0, minus infinity, whatever we're calling it for Q. Assumption, the degree, and this does not divide the degree. Yeah, fine, okay. So D is not 0. Definition of characteristic. Oops, we should probably go back and look at the definition of a characteristic at some point. P is irreducible. Yeah, that can't be equal to P times a polynomial. I was worried about this irreducibility thing where if the product of that like highest power thing hit up against the characteristic, then you could have this case where no, it's nonsense. Yeah, coefficients would somehow. No, okay, I don't really get it, but I want to get to the definition of separable down here, so that I'm picking up the definition. I think understanding the definition might help understand why this is happening, right? Irreducible polynomials have no multiple roots. It's a pretty good thing to say. But you sort of think about irreducible polynomials as not having roots. But I think we're talking about no multiple roots. Imagining that. What am I supposed to imagine for no multiple roots? Back up a step. We're imagining having like no multiple roots over L, the larger field, I think. Yeah, so we want to talk about if it's irreducible in K, it might be reducible in L. Yeah, it might be reducible in L later on. I know there's no L in 3.6 down here, and these ones don't have. But we had a thing up here about being no multiple roots in K is the same sort of thing as having no multiple roots in L. It's a bit like saying if you've got no multiple roots in reals, then you don't have any multiple roots in the complex numbers, which is actually slightly non-trivial in a way, because if you have no roots in the reals, then you just can't see in the reals where your complex roots are going to be at all, because you have no roots in the reals. Actually, I know they appear in complex pairs, and if they were, anyway, I know other stuff about reals and complex numbers. Okay. For my polynomial rings, I'm hoping that some of this is a little bit more obvious in the real complex number kind of case, which I think is where we're going to find the quintic, where that lives. Okay, 3.7. Let L over K be an algebraic field extension. Okay. You say that L over K is separable if the minimal polynomial of any element of L is separable. Hang on, what was a separable polynomial? Did we just have this? What? What? What would it mean for the minimal polynomial to be separable? Minimal polynomial is separable. If K is a field, all algebraic extensions of K are separable. But yeah, okay, so this is what I want. Any irreducible polynomial with coefficients in K is separable if characteristic of K is 0. These are the ones I like. Degree is prime to characteristic of K. Okay, so we're worrying a lot about characteristic 2 and 3. Later on, I think I saw something in the cubic formula bit about 2s and 3s. Anyway, minimal polynomial over K of any element if L is separable. What's a separable polynomial? Is that something I just supposed to know? Oh, if its roots are distinct in an algebraic, hang on. It has no repeated roots, right? The number of distinct roots is equal to this degree. Okay, so is this like, am I supposed to know this because it's, wait, it's up here. P of x is separable if all the irreducible factors of P have no multiple roots. What about the reducible bits of P? Except for the ones that you do have. Okay, I'm going to read that as separable as if it has no multiple roots, but that's not quite what it says. Okay, minimal polynomial over K if any element of L is separable. And this is apparently just true for all kind of rings that I care about. All the algebraic extensions are separable. Algebraic extensions are ones where you've like done something like adding in a root, and so there is a minimal polynomial for every element. So the thing that I want to build here, okay, I want to see this in action, I think, to understand why that separable polynomial is like that. All the irreducible factors. Okay, let's put this on this page. Separable polynomial. P of x. That means that all the irreducible factors of P have P prime equals the ideal generated by 1. No repeated roots. No multiple roots. No multiple roots. If, and okay, and I want to write down this thing about characteristics so that I remember that this is like, and then if characteristic of k is 0, then irreducible polynomial p of x is separable. Okay. Any irreducible polynomial with coefficients in k is separable. Okay. And there's a lemma down here. If M over L and L over K are algebraic field extensions. Oh, let's get down an algebraic field extension is separable if minimal polynomials are separable. Algebraic field extension is separable if minimal polynomial is always separable. Again, my notes, not very precise, lecture notes, very precise, but I like having both, so that I've got something in my own words that's not very rigorous, but is at least kind of helpful to me along the way. Okay, 3.8 here, m over l and l over k, both algebraic, and m over k separable, then m over l and l over k both separable. Tower law, no, not the Tower law. Something like the Tower law. That's not really the proof, but let's think about what it means. So for this to be separable, it says your minimum polynomial over k is separable, kind of no repeated roots. So m over l would be, okay, show me the minimal polynomial of m. They're both algebraic? I suppose they have to be, right? So algebraic means that each thing's got a minimal polynomial. So the minimal polynomial for a thing in m over l might just be, well, l contains k, so use that one. Use the polynomial in k. And l over k also contains k, so why not use that as the minimal polynomial? Let's read this because it's only a few lines, famous last words. M in M, let p of x be a minimal polynomial over k. Let q be the minimal polynomial over L, which might be different. By assumption, q divides p, right, okay. Q is the minimal polynomial of L. Maybe you get a better polynomial in L, even more minimal. Oh yeah, sure, okay. So L contains k, so it's this minimal polynomial is going to be at least as good as the one, at least as minimal, more minimal maybe, than the one that we had from k. Maybe L unlocks a new, even better polynomial. We don't know. But Q, this minimal polynomial over L, is going to have to divide P, the one that we had. It's going to have to be at least as good as the one that we had for P. Things here are dividing each other because everything's a principal ideal domain, so you take the highest common factor and the ideal is generated by something. Again, P has no multiple roots over K because P was the minimal polynomial in K. Over here, there's no minimal roots, no multiple roots over K. By, oh gosh, 3.4, P of x also has no multiple roots over L. Right, that's the field extension sort of one. If you have no multiple roots over the reals, then you have no multiple roots over the complex numbers or something. Finally, by kind of 3.5, Q also has no multiple roots over L. So it's separable. You take each of those and you're moving them up a level. You're moving them up a level. Since M was arbitrary, this thing's separable. So given m over k, k over L algebraic, if ml, I want to go mlk, don't I? Like the notes. Did the notes go mlk? Martin Luther King. mlk. M over L and L over K. Algebraic, if M over K is separable, then M over L and L over K are separable. That's terrible handwriting even for me. One more go. Okay. Where are we? There we are. Finite extension which is not separable. KBF2T, where F2 is a field with two elements. Ugh. Okay. PB x squared minus t. X squared minus t. K is, hang on, F2 of t. So the field of fractions. Since Px is degree 2 and has no root in K, it's irreducible. L be K quotiented by the ideal generated by P. Since P is irreducible, L is a field. Oh gosh, so the irreducible element generates a prime ideal. Prime ideal's maybe maximal here. Oh, there's a field now. On the other hand, P prime x is 0. So, I don't know. Yeah, because a field with two elements is really weird. 2x minus 2x would be equivalent to 0. Px is not a minimal polynomial of, oh my goodness, x mod px in. Oh my goodness. So kind of structured in a strange direction, this demonstration. Where's p the minimal polynomial of that? X squared take a big t. There's no t in there. What are we doing? What's t? Okay, I don't understand this at all. Something to come back to. Not on the first pass. End of lecture 3. And that will take much more than an hour. Okay. I'm going to take a 5-minute break. I don't have the ability to roll an advert, and wouldn't want to even if I could. We're going to do simple extensions in 5 minutes time. I'm just take a break. I'm going to make more coffee. I think I need more coffee. Yeah, more coffee. Right, back in 5 minutes. don't really know if you can do coffee breaks on Twitch. Does that work? It doesn't really work. Yesterday when I took a coffee break, well, let's say it was not good for viewership in a way that I thought maybe it might have been. You know, surely rather than watching maths, people would rather watch just the words "back soon" on a screen. Who knows? Right, okay, I'm back. I'm chipper. I've got coffee. I feel like today, while I was boiling the kettle, I thought, why does today feel so different from yesterday, right? I think yesterday was more, well, familiar to me, and also we could kind of always had more examples to work with and we were building more things. Whereas so far everything's super abstract. We haven't had any examples of things going on yet, and I don't have the experience to kind of build those examples myself yet, really. We're proving loads of things about field extensions, but the only one I'm referring to is C over R, which I'm hoping is relevant. I've got this new one now, but this just seems really odd. It's a finite extension which is not separable. It seems like it's here to prove a point. It doesn't feel normal in some sense. So I'm hoping that at some point this kind of comes into focus and we get sort of applications. I know we're going to end up at the Quintic, right? But we're kind of in this marshy space, right? Like in the bit of the Lord of the Rings where they are stuck in the marsh with Gollum for ages. It's a very literal metaphor. So back to the map. Sorry. So what we discovered over here is, if I move this logo label out of the way, so this kind of Galois theory over here. What we've discovered in this kind of region over here is a kind of marshland of definitions and setting things up, what it means to be separable. So how do you draw a marsh? I guess you do little bits of grass and some like fetid pools. No offence to these lecture notes, or especially no offence to the lecturer who's done a great job of writing the lecture notes. Just I know this does come together, right? Because it comes together to the Quintic. The reason it feels different from yesterday is more of a kind of marshy feeling of lots to learn, lots of definitions, which doesn't yet feel like we're standing on a mountaintop. A lot of the times in the rings we were standing on the top of a mountain looking down at, brilliant, okay, we see now, here's the example of a field extension that generates the complex numbers. And we haven't got there yet. We're in the bogged down a little bit. I think I've got a bit of a head cold as well, which is not helping. Coffee. In this kind of marshy area, eventually I think we're going to climb some mountains and get to see from a distance what's going on here. At the moment, to be blunt, it's not clear why the separable extensions are important or interesting. We've got some definitions and finite transfers across multiple field extensions, and it's something to do with multiple roots, I guess. So kind of relevant, I suppose. If your polynomial's got multiple roots, then things are a bit different, maybe. But that's not been applied to anything yet. So we're kind of 2 hours into this morning, and apparently 3 lectures, and yet to sort of grasp why this is related to the Quintic that I'm looking for. But that's okay. I think we've got a bit more of this. Let's look back at the kind of contents page at the front. I'm on page 15 at the moment. Where am I trying to go? And again, full respect to the lecture notes being like, there's a lot of stuff that we're going to need to learn. And I think this way of laying it out, where you have the theory first and then the applications, is like the sensible way around if you want to do several applications, or if you want to teach things generally. The kind of gimmick for this live stream is that I don't really care about the Quintic. I'm just trying to catch the Quintic. So whenever I'm learning something, I'm like, but what's this got to do with the Quintic, right? How does this get us closer to understanding Quintics? And luckily, so I'm at simple extensions right now. I've got a bit more theory to learn, a bit more marsh of. It feels bad calling it marsh now. Simple extensions and splitting fields and normal extensions. And I assume we're going to need all of this to understand Galois extensions when we get to page 21 and things get really exciting around page 24. Fundamental theorem of Galois theory sounds very good. And of course we're going to need all of that to do even more extensions. I guess more field extensions than I was expecting. Maybe that's just what's going on, that we've got to get to grips with what it's like to do a field extension, because everything around adding in these roots is going to be a field extension. Okay, maybe we need to get happier about field extensions in general. Field automorphisms of F, the smallest subfield of C which contains the roots. Doesn't feel like an extension at the moment, but I guess. Yeah, radicals, extractions of K roots, maybe the sort of things that give us field extensions later on. Maybe we'll talk about whether those things are separable or not. Okay, back to page 15. Feels like good progress though. There's a chance that today we skim through the things that we want to know and get more of that kind of joined up thinking. I'm also stalling for time because I've seen that this K thing here looks really hard to understand. So I'm armed with, and my axe, right? I've got coffee, I've got as much time as I need, and I've got notepaper. Here we go. No one said this be easy. Right. So let iota be a field extension from K to M, so M over K, and let S be a subset of M. Okay, so I'm going to draw a little diagram so I remember which thing's which. K, and then this whole thing is M, and S is some sort of subset within M. Okay, let's do a smaller subset because that's most of my picture. S. Okay. We define K of S to be, oh my goodness, the intersection over all possible fields L. L is supposed to be in M, but containing S. L is supposed to be bigger than I of K. What was I of K? Is surely just K, right? No. Hello. Subfield of M. This is a subfield of M because it's the intersection of loads of fields. Subfield M. It's called the field generated by S over K. So I guess S is possibly going to be my subset of roots of the Quintic. So I've got to understand this, right? Simple. Generators. Okay, we can do this. So we want a field that includes all of the things in S. So this field includes the things in S, and its field is a field, so it's good. Why would we do this intersection over all possible fields? Let's come back to that. And it's in M. Subfield of M generated by S over K. What is this? I of K. Iota of K. This is field extension. Oh, is this technically... Right, technically K is not in M. Technically this is like... This is technicality, isn't it? M contains a copy of K, not actual K. Okay, I'm going to think of this as K is in L. I don't like the way these are all written forwards and backwards. It's interesting, it's got to include kind of K as well. Okay, so you show me some roots of your Quintic or whatever, and try and generate a field over that includes all of those. Then you want to look at all possible fields, all possible fields in M that include that set and the field that generates things like the identity. Oh, okay. I'm going to make sure it's got the K structure in there as well. Yeah, okay. This is kind of, I think, making sure it's got the K structure so that it's a field extension of K as well. Field extension M over K is the composition of the natural field extensions. KS over K, yep, right, okay. It's a field extension of K, and M is a field extension of K of S. Right, and now those separable facts are starting to look like they're about to be relevant. Note that if, elementary fact, if S is this set of finite number of roots or something, I'm going to call them roots, then big K of big S, that set, is, what is this? This is do the thing multiple times. Coffee. First with S1, so something like take just one of them, include that, and remember to include the image of K, stay in M. Okay, and then take that field, which is not K, so the K notation over here is to say, well, okay, it's field over K, is a field extension over K. To take that and then do a field extension to include S2 as well. So this reminds me of the field extension that we were doing to include a particular element. Yeah, I do one at a time. Okay, right. So it's this notation means something like start with K and then do a kind of field extension where you're aiming to include particular elements of, you've got a large M. So yeah, I guess yesterday we had a way to do a field extension where you just threw in extra elements and you saw what you generated. Maybe by thinking about roots of polynomials. Oh, not that way, that way. There we go. Here we're thinking about you've already done the field extension out to M, maybe it's complex numbers, and you're now trying to build kind of the smallest field that contains all of, smallest field. This like intersection over Emma field is doing this kind of smallest field. Smallest field in M that includes all of those elements. You can put them in one at a time, extending one at a time if you like. Okay. We say that M over K is a simple extension if there is an M in the big M such that M is just one single element. Okay, a little bit stressed, but we got there. So C is a simple extension over R because it's the extension if you just add in I. Is that your example? Examples. I want some examples before I put this in my notes. I want to get more understanding. K is Q and BQ of I and root 2. We saw this sort of stuff yesterday. Field generated by I and root 2 in C. M is simple. Oh, and it's generated by I plus root 2. Interesting. I wouldn't have guessed that. How does that generate things like I? Right, okay. Simple algebraic extension of... We're saying algebraic a lot, I'm just going to ignore that word for now. Generated by I plus root 2. How do you generate stuff with that? As a field? Oh, what's the inverse of I plus root 2? So to make a field, you're going to have the inverse of this. And the inverse of this, I believe, is going to be I minus root 2 or something like that. Okay, let's work out the inverse in terms of just complex number arithmetic. What is this? So if I multiply top and bottom by root 2 minus I, then I get upstairs root 2 minus I, and downstairs I get 2 take away 1 is 3. But then 3 is in Q, so I've got to respect, because I'm including K in my field, I'm going to have to include the Q elements, which means I can multiply up to get root 2 minus I. So root 2 minus I can be constructed. And then adding that to root 2 plus I gives me root 2, well 2 root 2, plus gives me 2 root 2, and subtracting gives me I, 2i or minus 2i or something. And then you can make root 2 an I. Okay, so this field generation stuff is much more complicated than just doing like multiples by integers or something, which is kind of my mental image, I think. If I say generate by 1 and I, then I'm imagining like generating the Gaussian integers by just building some sort of lattice. But actually this shows that the thing here, I guess just q with root 2 is already pretty complicated, because q with root 2 includes well, all of q, which kind of is dense, and those root 2 things which fit in like 10 minus 13 root 2 or something. Let's pick a more exciting one, like 14 minus 10 root 2 is pretty close to 0. So these things are also, these new things are also kind of dense in there. So just imagine quite complicated sets for these. If you throw in I as well, then you get those things rotated and translated. So you get this kind of dense picture in the arcad diagram. Maybe it's not surprising you can generate all of that just by starting with I plus root 2. Okay. Field generation, pretty wild. Oh my goodness. Field of fractions of polynomials in Q. I have not got description of what this is. And a KB rationals. M is a simple transcendental extension of K. Oh my goodness. Generated by X. Note that X is transcendental over Q. So that's an element of it's an element of the field of fractions, I suppose. Oh, and in the field of fractions of Q of X, it has an inverse. 1 over X. Looking at all rational functions now, right? I think we really are. So including all this junk like this. X is transcendental over Q. There's definitely no polynomial. Has solution X? That'd be weird. It's like the opposite of school algebra. X as a polynomial. Huh. So maybe I should be thinking about these polynomial rings as extensions? No, they're not fields. The field of fractions of polynomials is a field extension over Q. So this must be huge field extension. Generated by X, because that lets you build polynomials and 1 over X. Go for it. How do you build 1 over X squared plus 1? Build X squared plus 1 and insist that its inverse is in there. Okay, so simple extensions are things generated by a single element. And it turns out you can do that quite often. These examples are both way more complicated than I thought they were going to be. I wouldn't have minded up here. Keep with root 2 it's fine. Oh, this is the field of fractions as well. So we're supposed to be generating inverses of these things as well, but that's fine. Okay. If you're building a field, then that's going to be okay. Yeah, I suppose I should remember this. We're generating fields, so often we want to do the field of fractions rather than just writing down the ring. There's kind of this ring that's generated by like a plus b root 2, but that's not a field. It has a field of fractions. Okay, so we're often moving to the field of fractions rather than just the ring. Feels like understanding. I'm not sure what I've understood, but yesterday felt like a lot of these nice rings with like a and b integers. Not a field, but we can make a field. Field of fractions. Okay, I appreciate field of fractions slightly more. Okay. Proposition 3.9. Right, I feel like I should make a note though on separable simple field extensions. Simple field extensions generated by a single element. Is that what I'm going to write down? Yeah, I think that's what I'm going to write down. I don't really want to write down this. generated by. Yeah, okay. I'm going to put generated by in my notes. Reminder, every time we look at my notes are not the lecture notes. My notes are not good. We're going to delete this page because it's always in the way. It's some scribbles from yesterday about how something is not a principal ideal domain. How do I do that? Delete this page. Yes, delete this page. Good. Okay, and we're going into my notes for today. Notes for today over here, which look like this. So, simple extension is, I'm going to put generated in quotes by one element. That's what makes it simple. Okay, not fully, rigorous in any sense. Don't have that big intersection sign, but whatever. Okay, 3.9. K of alpha over k be a simple algebraic extension. Fine. There's alpha algebraic, so there is a minimal polynomial. Let p of x be the minimal polynomial. Then there's a natural isomorphism of k extensions. Yep. Okay. Polynomials in k quotiented by p of x looks like m by sending x to alpha. Oh, this is like plugging in alpha into your polynomial, right? So the kernel is polynomials that give you 0. If you quotient by that polynomial, then you'll get the image, which is the image all of m. Yes, because m is anything you can make field of fractions with alpha in. I can't remember that's field of fractions. It looks like polynomials, right? Because round brackets. Everything you can make. Existence of manifold definitions. Since p is non-zero, we call it alpha is algebraic over k. Yep. That's a maximal ideal. Fine. Okay, good. Exciting. Thus, the image is a field. No, that is cool, actually. That is cool. With like I and the R question by I sort of fact. Huh. By the definition of M. Sure. Okay, so this is the assertion here that I was trying to find in words. This thing is constructed to be wait, which bit of that is M? Is M just K of alpha? Field of fraction of... Yeah, fine. It's all the stuff with alphas in. Okay, seems reasonable. Okay. Under the assumptions of the proposition, so in particular that the degree of the field extension is the degree of P. Yeah. And the vector space is kind of what you... The basis is what you want it to be. Always just plug in alpha and reduce stuff. This was the sort of field extension we were doing yesterday, where I put in one thing at a time. They were called simple field extensions. We now know. Okay, we learned a thing about yesterday. We can go back to yesterday and label it simple field extension. And there's the basis that I kind of wanted it to be. If you've got a particular polynomial that's the minimal polynomial, you can reduce any other polynomial down towards that by doing some sort of replacement stuff. 3.10. Let M be K of alpha over K be simple algebraic extension. Yep, okay, by putting in an alpha, make the field of fractions. Let P of x be the minimal polynomial of alpha over K, and then extend K. Okay, we're extending K, so we did the field of fractions of polynomials of... I'm pronouncing that as field of fractions of polynomials of alpha. Is that right? It's kind of the field extension of alpha than the field of fractions of that. I think I want to understand a little bit more that notation. I'm worried I'm not pronouncing it right. Right, K goes to L, extension of fields. P of x minimal polynomial of alpha over K. Then the maps of K extensions M to L in one-to-one correspondence with the roots of P in L. Ooh, proof clear. Thanks. maps of K extensions. What is happening here? M to L. The maps of K extensions from M. Where are the maps going? The maps of K extensions. Oh, no, what? The maps, are they automorphisms? From the K extensions? And they're in one-to-one correspondence with the roots of P in L. The maps of K extensions. Is the phrase K extension describing these things? This is supposed to be a corollary of the thing we were just reading. P of X minimal polynomial. If K, there's a natural isomorphism from polynomials of K quotiented by P to M. So now if you go to L, extension of fields. It says let P be the minimal polynomial of alpha over K twice. So that's not helping me. The maps of K extensions. No, yep, don't get it. Don't get it. I don't know anything about the roots of the minimal polynomial in L, right? Do I think that X is a root of a minimal polynomial in? I think X is a root from what we did yesterday. I think X in the X bar thing, the coset of P. And then the maps of K extensions M to L. Doesn't mean anything to me, sorry. The roots of P in L. Okay, well, it follows from 3.9 that a finitely generated algebraic extension is a finite extension. Look at the degree or something. Here's an example. Field of fractions of Qi in C. Isn't the field of fractions of Qi just... I really think I might be saying field of fractions too much. We're using round brackets for our field extensions today. Are we using round brackets for field extensions? I think we are. Back up. Are we using round brackets for field extensions? For when you field extend with one thing, we are. That was what the simple ones looked like. Finding the notes. Finding the notes. Finding the notes. The facts about rings, and then we saw. I think I might be saying field of fractions too much. Those things where I was dividing by 1 plus I, you can just rewrite those as, it's not different. It doesn't matter. For that case, it doesn't matter because those are the same set. But I should understand what the round brackets thing means. I've got to find the field extension notes. Here they are. What are we doing today? I haven't got a field extension yet. Field extension with just an element? Like the simple field extension. It's the thing I was just reading, isn't it? It's the thing I was just reading. Good times. We need to be way past page 15, don't we? At this simple extension. It's the round brackets for simple extensions. Simple extension. Round brackets for simple extensions. Good. Okay, we learnt the thing. Always get the notation. Day one, well, day two, I guess, but day one of Galois theory, getting the notation down. This was my notation for, or the notation for simple extensions. So that's pretty good. Up here, this is the extension then with two elements. So not field of fraction stuff. I don't know what's going on down here. Oh, that one is field of fractions. Oh my goodness. This is what's thrown me. Round brackets around an x is the field of fractions. Round brackets around some elements means the simple field extension, or the field extension over this set, which might turn out to be simple. But that one's field of fractions. That one is not. Are you using too many brackets, right? So this one, to make that into a field extension, was looking at the field of fractions. Over here, this thing's not field of fractions. This thing's just thrown alpha. I had this exclamation mark just down here to say I think I don't understand what alpha is, but now I'm taking away the exclamation mark. So no field of fractions, just throw in alphas. Still doesn't help me understand it, does it? Now extend K to L. Extension of fields. Wait, was that within M or something? No. Maps of K extensions from M to L. Oh gosh, okay, so M is where K kind of like lives, right? So oh no, it's the set. So this really is the set that's like over K. So maybe if K is the field like Q, and then maybe this is Q root 2. So Q with root 2 over K. And then P of X is the minimal polynomial, which is x squared minus 2. And then think about extending K further, or extending K in a different way. So QL over Q like this. Extension of fields. Then maps of the K extensions from M, which was a K extension, to L are in one-to-one correspondence with the roots of the minimal polynomial. That's so mysterious. Maps from M to L. Okay, so roots of Px in L are going to be maps of the K extension. You've got to send root 2 somewhere. You've got to send root 2 somewhere. You've got to send root 2 somewhere. And then the minimal polynomial kind of lives in Q, which is the set K in this statement. Is that going to be a root? M to L are in one-to-one correspondence. The roots of P of X in L. What could that possibly mean? If you've got some roots, then. If you've got some roots of P of X in L, you like how Q of root 2 has roots of P of X in L? You've got to send root 2 somewhere. Maybe just send it to a root, right? Because it's going to preserve that the polynomial sort of carries over. The map of K extensions is going to be nice to multiplication and addition, so it's going to be nice to your polynomial. So when you try and evaluate P of alpha, that's going to go to 0. So so P of alpha is going to go to like P of question mark by K extension stuff, but also P of alpha is equal to 0. So it's going to be, and 0 is going to have to go to 0. So this thing is going to be a root, the place where you send alpha. What's that got to do with the maps? I guess we could talk about where you send alpha. Why is minus root 2 come into this, right? There's another root of P of X in L. Oh, it might not be in L, or it might be in L, or it might not. Okay, I'm getting a bit closer, but still not certain what's going on here. Okay. Oh, hello. We've got an example. I should be reading the example. MB QI is a subset of C with rational coefficients. So complex numbers with rational coefficients, and let K be the rationals. Now let L be rationals of root 2 over C. Okay, which is all reals, right? Then there is no map of k extensions from M to L. You can't even send I to 0. There's no map from M to L because the roots of x squared plus 1, which is the minimal polynomial I, do not lie in L, which is all real. There's no map of k extensions. Is it not a good idea to send alpha to... You can't just send it to 0. You can't just send it to 0 because then it's a unit. So what are you going to send its inverse to? What are you going to send 1 over alpha to? In order to get the products to go to 1. Okay. I'm still getting used to field isomorphisms or field homomorphisms, maps that preserve that structure. They're pretty good. I think I've just realised they preserve sort of polynomial stuff, which is important. We had a bit of that yesterday for when we had an f being applied to something really complicated like x bar plus the ideal generated by x. We worried about that quite a lot. Okay, L is the complex numbers, M is the above. Then there are 2 maps of k extensions M to L. L is C. Okay, which correspond to the 2 roots of x squared plus I in C. Right, so I guess this is claiming you can send I to either I or minus I. It's kind of like this permuting the roots idea. Not quite. That's a simple extension. So there's only one thing. You're going to send it to... You've got to send it to one of the roots. That's kind of it, isn't it? You've got to send it to one of the roots. And if there is no root, then you've got no options. But you've got to send it to one of the roots. And then afterwards you're fixed. Because now you know what you're doing with everything. That's probably it. Okay. Maps of k extensions M to L. Okay. Okay, different extensions. These maps are not really doing permuting stuff because kind of a little bit. So if you've got like the cube root of 2, you can choose which root to send it to. If you're doing like something over the reals and q augmented with the cube root of 2, choose where to send it. Okay. What do we have in the notes for this? So in rough notes, simple extensions generated by one element seems good. What was the other thing we talked about? Oh, separable. Didn't really get separable. Kind of no repeated roots, right? And preserved over intermediate field extensions. Yeah, that was separable, right? A separable polynomial is one where the irreducible components have no multiple roots. Separable extension if the minimal polynomial is always separable. That was where I declared myself to be stuck in a marsh. Right, splitting fields. One more sort. Is it one more sort? 3.4. And normal extensions as well. 3.4. Let K be a field. I like these end of lecture markers. It's a really good way of tracking progress. It shows me that, what have I got to do? I've got the splitting fields to get to the end of lecture 4, and I've now slowed down to, we did half an hour, 40 minutes, and now about an hour or something? 9 to 9:30. 10, yeah. Slowing down on each one, it's good. I do that slightly, sorry. 9 we started. 9 we started. 9:30 we were like, brilliant stuff we've done. 9:30 we've done lecture 1, we started lecture 2, and then I think it was about 10:30 that we started lecture 3. We're still on lecture 3 and it's 11:30. So we're looking at, no, it's 40, anyway, never mind. We'll check the VOD. Splitting fields. So let P of x be in kx polynomials, and we said P splits in k k is a field, if for some c and k and some sequence of ai's, we have, oh wait, this is like factorising, right? Splits looks like factorising to me into these things. But it's not. So the stuff we've had about factorising in irreducibles has involved quadratic components and something. Hi again, Ashwinder. How's your break going? That's all I type because I think Ashwinder's got me. I'm getting bogged down in different sorts of extensions. I've learned that people can join chat without joining audio. I can't imagine watching a live stream without audio, but apparently it's an option. Okay, so we've got this definition now of a splitting polynomial, if you can put it down like that, which you can, in C, you can always do for polynomials, right? Polynomial splits if you can write it like that. Let's put that in my notes. Collecting my own stuff. Oh, you got audio, hooray! Welcome to the live stream. Did you find us from typing maths into Twitch or something? Or are you here for the Galois theory? Those are the two options, I think. Either intentionally looking for Galois theory on Twitch, or here for the Galois theory, right, cool, yeah, here's the Galois theory. Good. Yesterday we had some viewers who were just, and I didn't know people did this, typed math into Twitch and then watched whatever stream came up, which surprised me. If you're one of those people watching, then hi, great to have you with us. There's some Galois theory on today. That's nice, isn't it? The polynomial splits if p of x is equal to c x minus x I think we're calling them ai, product over the ai's, product over I guess, for some c and ai's. Okay, my notes are very rough. Trying to give me some notes for. Hi from Matt. Hi from my job. No, in a nice way. I've been really struggling today. Let me show you the map. I don't know if you saw the map before. I'm going to talk to you because you're here. Here's the map of what I'm trying to do. It's like a kind of Lord of the Rings adventure. We started over here. Group theory, which I associate with kind of like friendly elves and helpful things. Groups are lovely. Vector spaces, which is kind of dwarven mine over here. We've gone on this journey yesterday through this kind of mountain range of rings, which on one sense terrible because you've got to get through the mountains and fight a Balrog and stuff. But on the other hand, pretty good because you get a nice view from the mountains. While we were up here, we saw the kind of lava pits of the field extensions. We saw what field extensions were going to be like. Then we came down and got bogged in and got into this kind of marshy bit, like in the bit of Lord of the Rings where they go through a marsh for ages. We're now learning about different sorts of extensions. There are kind of three that are signs that we're getting close to the Quintic, where we're going to eventually learn about cyclotomic extensions, chimeral extensions, and radical extensions. Those ones are extremely relevant to the kind of Quintic stuff that we want to know. And I happen to know that around the kind of Quintic mountain, there's this little forest of group theory stuff again. The elves come back. That's kind of the story that we're trying to piece together. We are firmly in the marsh of understanding different sorts of extension. We haven't got very many examples yet. We're just learning different types of extension. I think these are all going to correspond to different things that you could do while you're trying to build a Quintic formula. So you try and augment the rational numbers from your coefficients. You try and augment those in various different ways, but those ways corresponds to some sort of symmetry theory about the roots of the Quintic, which why you've kind of failed. The roots of the Quintic have bizarre extra properties from the symmetry group that you cannot do with these classes of extensions which we're describing. So we're being quite, I suppose, systematic about going through different sorts of extension. I don't quite know how they correspond yet to the kind of symmetry theory. There's some stuff that we've just seen about how this so-called simple extension, where you just throw in one root of a polynomial or something. There's some one-to-one correspondence with the roots of the minimal polynomial. So like extending to C. whenever I say field extension, I mean the thing to have in mind is the way that the complex numbers are an extension over the reals. You start with the reals, and then you throw in an extra new idea, I, which gives you this new picture of higher dimensional thing. And it's literally higher dimensional. It's got this two-dimensional structure. But it's not just throwing in I. We could also imagine in throwing in things like root 2 instead, or as well as. If you throw in root 2, then you can generate these other interesting numbers by doing algebra involving root 2, this kind of absurd stuff, manipulating square roots of 2. We're thinking at the moment about throwing in just one thing at a time, to see what happens. We've seen earlier on this page, though, that sometimes if you throw in I and root 2, that's the same thing, if you're clever, as just throwing in the number I plus root 2. Kind of all works out. You can build the other stuff using kind of linear algebra, which is kind of cool. And now we're getting bogged down into what a splitting field is. So x squared plus 1 is an example of a splitting polynomial because you can split it down into these linear terms. So I'm going to write that as my note here, split into linear terms. A lot of what I'm doing today is to try and get the notes, which are very technical, and write some of it in my own words, which are not technical, so that I've got both the kind of technical headspace of here's what it literally means, and also more of the heart space of here's what it feels like to me. Can split into linear terms, can do something. It tells you can do something. It's positive. It just means nothing in the black and white of the notes that says it's positive or good, right? But I'm going to pretend it's good. Okay, a field is algebraically closed to like the complex numbers if any polynomial with coefficients in L splits into L. So it's true for C, but not true for Z or something. Here's the example. If P of X is irreducible and the degree is bigger than 1, then P of X has no roots in K and does not split. Okay, good. Proposition 2.9 ages ago was about irreducible things having no roots, I think. Quick look back. The nice thing about these notes is that every reference back is a hyperlink. So I'm going to have a look at 2.9. K to field, and let this be that. Then, yeah, factor theorem. And then the kind of decomposition stuff. Right, good. Okay. Can I go back? No. Let me go back very quickly. Okay. PDFs, not all they're cracked up to be. Okay. I'm oscillating today between whether PDFs are overrated or underrated. The hyperlink thing's very cool, but not being able to go back arbitrarily is quite annoying. It's not quite a web browser, right? Maybe that's good. Field extension M over K is a splitting extension. This is a definition. Less precisely a splitting field. Okay, extensions are a special class of field because they extend over a particular field that's a subset. For P in a splitting extension for a polynomial P. A splitting extension for P. If P now splits in M, and M is generated over K by the roots of P of X and M. Ooh, okay, so like C over R. Yeah, so introduction to Galois theory, yeah, you need to know fields before you start. The only things you really, I hope the only things you really want to know about fields are that they're nice under addition and multiplication. You can divide, except dividing by 0, but they're kind of fine. You should imagine the rationals, the reals, the complex numbers, all these nice things where you can divide, but not the integers. That's the kind of distinction to draw. You can make things into fields, but not important right now. Okay. Field extension is a splitting extension if P splits in M, and if M is generated over K by the roots of P in M. Okay, splitting extension. So put this in the log. So much notation. Splitting extension. What's going to be my catchy thing for this to remember this? M over K, and then it's for a polynomial P. What's the wording we're using here? For P in K. A splitting extension for P, such that P splits in M. Splitting. Right, okay, so I need to rephrase this, right? So M over K, M over K, M over K is a splitting extension for P of X. Maybe I'll say it splits P if Px splits in M and M are generated by roots of P. Maybe I should say M over K. What did they say in these notes? No, they say M is generated over K. M is generated over K by the roots of P and M. Okay. So there exists. So theorem. We're skipping proofs this morning. I'm going to come back and learn them at some point. There exists a field extension M over K, which is a splitting extension for P. Just take the roots and go for it? Probably. Induction on degree. Right, okay, let's not read that. So if you have a polynomial, then we can do a field extension that splits that polynomial. We can break it down. We will find its roots over anything, not just for like real sort of complex numbers, right? Ooh, I like this. Show me any polynomial over any ring and we can field extend to get solutions to that. Okay, this is powerful. Kind of a little bit for R and C. I think this is going to be a bit repetition of something. Like it's always C, right? Or maybe not always C, but it's always a subset of C for real polynomials. Okay, if L is a splitting extension for P, then L and M are isomorphic. It's M? Okay, I think it's just saying there are two of them. If you have two, then they're kind of uniquely defined. Work out where the roots are going, probably. And 3, L over K is a splitting extension for P, then J over K be any K extension. The images of all the maps of K extensions from L to J coincide. This sounds again like the thing about looking at where the roots go. That's all I've got, right? The roots of P of X in M are one of the only objects around. And it's going to be some sort of like ring stuff. I'm going to have a look at the proof, but not all of it. Oh, there's quite a lot of proof here. Right, so induction on degree P. Suppose the degree is bigger than 1 of the theorems we have. Induction time. P1 being an irreducible factor of Px, something that you want to split. Then do it like this. Look at your polynomials and just quotient by that. M1 is a field. Yep, there's a natural map of rings making a field extension. Yep, okay, look at the constant polynomials. By definition, P has a root in M1 corresponding to X. We saw this yesterday. It was very good in that presentation. Oh my goodness, okay. Now let M be a splitting field for Px over X minus A over M1. What was A? Stumble. What was A? By definition, root A in M1. Oh, right, oh gosh. Oh, so first do it like this to get a splitting. First do it like this to get a field extension which has a root. Do a field extension to get a root, and then grab that root and do a splitting field over M1. That is pretty hardcore. It's 2, right? There's 2 steps. K goes to M, K is in M1, and then M1 is M over M1. So there's 2 steps here. That's hardcore. I kind of love it. First question your polynomial rings, and that's got a root in it. And now, abstract level, look at M1. That's a root of that polynomial now. Like how we assert that polynomials have always got a root in the complex numbers. This is just saying, well, do some quotienting and then it's got a root. That's amazing. By construction, P splits in M. Now, right, we've got to follow through the other roots. The beginning of subsection 3.3 and proposition 3.9. We built it up, generated by these roots, and it's built by so that's a bit of all the roots. So that's the kind of simple extension thing at the start of subsection 3.3. M is generated by k by its roots in M, so it really is. The roots kind of follow through. Okay, so building this like one at a time, but following through the roots, I think. Okay, read it in more detail at some point. Okay, 2 by induction on degree of P again. What was part 2? Part 2. There's only really one way to do it. These things are isomorphic. Take the roots and alphabet A be a root, and a Q of X splits middle polynomial, Q splits in M and also in L, so this divides P. If you root of P and a Q. Back up. Find a middle polynomial. Oh no, hang on. Is L just some random extension? Oh, they're both splitting extensions, I think. Notice that M over K of A is a splitting extension for P of A. Yep, okay, like before. Now let J be split the quotient polynomials over Q, since J is a field. J is a field because Q is irreducible. Ooh, further natural isomorphisms. K and A carry O1, root of QX and L, oh my goodness. J extensions up to M and up to L by the inductive hypothesis, oh my goodness. These two J extensions are isomorphic by some degree consideration. Construction isomorphism of these is also an isomorphism of K extensions, so we're done. That looks very difficult. Okay, and then 3 is about maps, splitting extension, and that's J be any K extension. So J can be huge. Images of the maps of K extensions coincide. Oh, the images of the maps, because these things are going to get sent to roots, and then the image is going to contain all the roots and be the extension over K in J or something. If there are no maps, then we're good. Here's a map. Look at the roots. Image of phi. It's generated for K by the image of the roots of J. These images are also roots of P of X and J. That's what I thought. To see this, we're going to do that. That was complicated. It's like following it through the polynomial, I think. Should I try to? Yeah, is it just following it through the polynomial? Sort of. What's sigma? Not sure what sigma's supposed to be. Why is it minus? What are these sigmas doing? Permutations? No? No idea what the sigmas are. What are these plus or minus signs? Sigma D. Oh, okay. Ashwin wants to ask about question 1 on the maths. Losing a lot of unnecessary marks on question 1. Oh, that's a shame. Sorry to hear that. I think I'm not going to give you any math advice. I'm really sorry. So I think you kind of know what to do. I think. So that's one of my reasons. The other reason I'm not going to give you math advice is that I'm technically on strike. My normal job is to give math advice, and I'm trying really hard not to this week. I think you'll be all right. I think you'll work it out. I think you could be more adventurous than just trying a lot of multiple choice questions, right? I always say, try other stuff. Try other questions. Anything where you're stuck on maths. It's a phrase I say a lot. Look at me doing my job when I'm not being paid to do my job. No, it's just talking about maths, isn't it? What are we doing? Set of roots of P and J does not depend on phi, hence the assertion. Yeah, maths homework and it's chill background noise, isn't it? I put "Let's study with me" in the description, which I think most people use as kind of aesthetic, chill stream. I'm not like that. Good. Note the following useful fact. K be a field and P of X in K. Okay. Suppose there is a field extension K up to L where L is algebraically closed. Let S in L be the roots. Okay, roots of P and L. Good, good. Field extension up to L. Then K, by those roots in L, is a splitting field for P. This follows from the fact that P of X splits in K of S because L is algebraically closed. If L is algebraically closed, does that mean everything splits? Hang on, back up. L is algebraically closed. If any polynomial coefficients now splits in L, algebraically closed. On here, L algebraically closed if any polynomial in L of X splits in L. Do you have to say it splits in L? Yes, I think you do. That's what these notes are going to say, isn't it? Splits in L. Yeah, okay, good. Isomorphism enhanced in 2 is not canonical. I missed that the first time round. Splitting extension P, then L and M are isomorphic as K extension. Not canonical. 2 looks really complicated, actually. Okay, splitting field for P of S. P of X splits in K of S since L is algebraically closed. Okay. If you extend up to an algebraically closed thing like C, then simply follows from the fact that P of X splits in K of S since it does, and from the fact that K of S is generated. Okay, so it splits. Show me the roots. From the fact that KS is generated by the roots. Well, yes, it was, wasn't it? And that's what you need to be a splitting field. Splitting extension, sorry. P of X splits in M. It splits in its own field extension thing. And M is generated, and it's generated by the roots. That's literally what it is. The simple extension is, I don't know what that's called if it's not one element, but this kind of subset extension thing is generated by the roots. It's algebraically closed. So it seems to rely a bit on being algebraically closed over here. If I assume that C is algebraically closed, then this is kind of good because I can skip some of this and just refer to all of these for the same thing. It can be proven that for any field K there is an algebraic field extension up to K bar where K bar is algebraically closed. The extension K up to K bar is unique up to non-canonical isomorphism. It's called the algebraic closure of K. We're not going to use this fact. Fine, okay. We hit the end of lecture 4 on I'm not going to use this. Welcome back, Field C. 111901. Everyone in chat's got 5-digit numbers. Where's my 5-digit number? Wait, that's a 6-digit number. So many ones. We're defining different sorts of extension fields. And we've got some stuff here about Q and C and extending from Q and C, which is exciting because that's exactly what we're doing when we're looking at the roots of the Quintic. We want to look for this kind of field extension out to the roots of the Quintic and talk about its symmetries, talk about permutation theory on that. Okay. What do I think? Yeah, okay, I'm going to take this for now. Normal extensions. One more sort of extensions. What's our overview here? So normal extensions. Trying to do something fun because people are in chat. Normal extensions. We've got a definition, a theorem, and then some proof and corollary and proof. And we hit section 4. At which point, I think that's got to be the end of lecture 5. Yeah, okay. So I think my aim for the next half an hour before I take a lunch break. Oh, I'm sure this is how streams work. Live streams all about scheduling your lunch breaks carefully, right? We're going to learn normal extensions on page. Sorry, a lot of scrolling up and down while I try and work out what's going on. We're going to learn normal extensions here. We're going to have a look at normal extensions, and then a bit more normal extension, and then we're good. We've got 2.5 pages before lunch. That seems reasonable. Then we can learn Galois theory, which I promised, skimming it this afternoon. Or have a look at what's going on this afternoon. Okay. An algebraic, is going to involve splitting. Okay, an algebraic extension. L over K is normal. So algebraic extension, everything's got a minimal polynomial. If the minimal polynomial of K of any element of L splits in L. Feels like it usually happens, right? Oh no, here's an example where it doesn't happen. So let's look at this example where it does happen, and an example where it does and doesn't, and these look quite similar, so this is going to be interesting. So the minimal polynomial of this is x cubed minus 2. Fine, Eisenstein's criterion, fine, and it does work. On the other hand, this thing is in the reals, and this has non-real roots, so it does not split cube root of 2. Oh gosh. Right, okay. So the minimal, so this extension, throwing in the cube root of 2, gains you a root of this polynomial, but it doesn't necessarily gain you all the roots of the polynomial. So we had this brilliant thing yesterday where we did, and it's come up today as well actually, midway through a pretty cool proof, that when you do a field extension you gain a root. So if you do a field extension you gain a root, but you don't necessarily gain all of the roots for your polynomial. On the other hand, root 2, you kind of do, because this field extension also includes minus root 2. Degree is 2. Ooh, minimal polynomial less than or equal to 2. We're trying to look for its minimal polynomial. Oh, anything's going to split. Fine, I actually know what its minimal polynomial is, so I don't really understand this. Kind of coyness. Do I like Star Wars? Yeah, Philsey says sure. I like Star Wars too. I even like the new ones, which are less popular. Although I do feel that the best bits are where Star Wars is kind of the same as the previous Star Wars films. Number 7 is the same as 4. And then isn't 8 also the same as 4? Or is it kind of the same as 5? I kind of lost track of it. The most popular thing they could do is to make 4 again. And they're going to keep making 4. If we keep watching them, then they'll keep making 4. Star Wars 4 forever. What we deserve is like Star Wars 5 forever. But in order to get Star Wars 5 forever, we're going to get Star Wars 4 forever. Good. Lemma 3.15. I should write down this normal extension idea. Minimal polynomial over K of any element of L splits in L. At the back of my mind, I also know that everything splits over C, so if I'm extending up to C, I might not be extending all the way to C. That's something I should worry about then, I suppose. When I said it usually happens, that was a missed opportunity to say a joke, but never mind. What was the notation here? It was like L over K. L over K. Algebraically closed. Algebraically closed if any polynomial L of x splits in L. So normal extension. If hang on. So I want an algebraic extension. Gosh, I need to start with an algebraic extension so that there are minimal polynomials. Algebraic extension L over K. Splits no is normal. Almost lunchtime. If L over K if the minimal polynomial always splits in L. I think. Let's have another look if I've got the subtleties of this down. The minimal polynomial over K for any element of L. Minimal polynomial over K of X. Oh my goodness. Okay. Splits in L. Sure. Okay. That's kind of what the minimal polynomial is supposed to be, I think. When you're talking about an algebraic extension. Got to go back and learn it all. Okay. Lemma. Let this be an algebraic field extension. Let J over K be a different extension in which the polynomial splits. Ooh, what is this? M subscript alpha I. Oh, these are the minimal polynomials, and you're producting them together. So take this sort of thing where you extend it over some random objects, multiply there together their minimal polynomials, and then extend up until you hit J, where that actually splits. There's a map of K extensions from M to J, and the number of maps is finite. Finally, if the polynomials are all separable, then there are degree such maps. Oh, nice. Nice. What was separable? I got separable and splitting, and I'm not keeping those separate in my mind. Separable. Separable polynomial, all irreducible factors, and kind of no repeated roots. In other words, oh good, the set of extensions of the map from K to J to a ring map. Oh my goodness, of the map. Extensions of the map K to J to a ring map M to J is finite and non-empty. And if all of the MI are separable, this has cardinality M over K degree. We're using the colon in our degree notation, fine. First and second session together. I'm going to skim the proof to try and get more of an idea of what's going on. Extension of the map to K of alpha 1. There are only finitely many such extensions. Each extension corresponds to a root of the minimal polynomial in J. You've got to send the roots of the polynomial to roots in J. Now note that the minimal polynomial of alpha 2 over K alpha 1 divides M alpha 2. Thus has a root in J, since N alpha 2 splits in J. Gosh. Skimming it, conclude again from 310 that the ring map, there's an extension of this map to J. A map of this thing into J. But only finitely many such extensions. Continuing this way, it's extension map this way. Only finitely many such extensions. Got to send them to a root. This feels like it's going to be a number of roots factorial though, right? Which is not really what degree does. Proof of third extension. Repeat the reasoning, computing degrees along the way. There are that many extensions just to get K alpha 1 of K. It's the degree of the minimal polynomial down there. Oh gosh, is this going to work out just because the degrees are going to work together? Of the map, degree of the minimal polynomial of alpha 1, find its degree. That's how many places you could send alpha 1 to. Oh, the things you're extending are not created equal. You can't permute them because some of them might be like root 2 and some of them might be like I. You've got to worry about sending them to roots of that the correct minimal polynomial. Goodness me. Okay. You got all this kind of like different structures that might be going on in your field extension, where you might have thrown in some cube roots and some square roots, and you can't just mix those up when you go to a different field extension. You've got to preserve things nicely, I think. Okay, so this many of them for that particular root, alpha 1, or number object alpha 1, that many of them extensions of the map to K alpha 1. This has no multiple roots, so that's the degree is how many roots it's got, I think. Oh, is it splitting? Minimal polynomial is, if we got something about it being normal somewhere. No, okay. Oh, J is an extension in which it splits. That polynomial splits, okay. Yeah, okay, so we're in J where this now splits, so I think we're now talking about counting the roots, I think. And not worrying about multiple roots. Okay. Oh, and then there's the tower law, which tells you that you should multiply those together. It feels like it's going to be much bigger than the degree, right? It turns out to be the degree down here, the degree of the field extension. This is about the kind of dimension of space. So when you go from the real numbers to the complex numbers, you go from a 1D number line to 2D space, the Argand's diagram. We're trying to look at what happens if you go step by step. So you talk about adding root 2 in, and you talk about adding I in, maybe separately. But that's not simple, that's fine. Any ring map K alpha 1, there are K alpha 1, alpha 2 over K alpha 1 degree of that number of extensions of the map to a map into J, and you should multiply them. Oh, okay, and then it kind of keep going until you get up to n. So what's the surprise here for me? I suppose I was expecting this next one to be the degree here. I was kind of imagining that to involve kind of stuff to do with alpha 2, but it also is kind of dividing by the size of alpha 1 in a way. Yeah, okay, so that alpha 1 there, what does that mean? You've got some extra degree stuff from where are you sending root 2 and then where are you sending I? Root 2 is going to maybe a couple of places if that polynomial's got degree 2. And then where are you sending the cube root of 2? Because I've put that in as well, let's say yeah, Q, let's imagine Q with root 2 and the cube root of 2. So I want to be able to solve x squared minus 2 and x cubed minus 2. And I've extended out to a field like C where that splits. A bit overkill, but maybe I should just have gone to R, but hey. R over Q is infinite, so it's daft. Those things finite somewhere? Oh, it's supposed to be an algebraic field extension. Oh, J is anything, right? Where the polynomial splits. The number of maps, though, into the reals. Okay, so it's fine. M over K is a degree, which I believe might be 6. If you do root 2 first, you've got 2 choices, and then you do root 3, and there are 3 choices. So you multiply those. That's kind of what's going on, isn't it? Degree 6. Okay. Extensions of the map K to J to a ring map M to J. To a ring map M to J. Oh, the map's getting extended because the kind of map is getting extended because once you've decided where K is going, M has to follow. Yeah, sorry. If you extensions of a map to the ring map. One more time. The number of maps of K extensions M to J is finite. Maps of K extensions M to J is finite. If the number of polynomials are all severable. If you're not worried about counting multiplicity, repeated roots, this is the bit where I might care about severability, like counting the kind of degree, the number of roots moving around. Okay, theorem. Finite field extension is normal if and only if it is a splitting extension for a polynomial with coefficients of K. That's brilliant. That's really good. Let's write that down. I'm going to skip the proof, I think, but I'm going to write this down. This is great. Finite field extension L over K is normal, if and only if it's a splitting extension for a polynomial with coefficients in K. Finite field extension is normal if and only if it's a splitting extension for a polynomial. If it's an extension which makes a polynomial split. Okay. So these ones where you throw in like root 2 and cube root of 2 are the ones, those are finite field extensions and they're splitting extensions, and that's what this is saying. Proof, take the generators. I said I'd skip it. Root row of J in the minimal polynomial. Okay. Image of lambda in L. Q has coefficients K and L. Lambda gives an isomorphism between L and the image of lambda. We see the Q splits in L, which is what we want to prove. Okay. Theorem 3.17. Okay, so now take a splitting field of a separable polynomial over K. Then we have the number of automorphisms preserving the K structure of L. If the splitting field of a separable polynomial over K is L over K. Apply 3.15 with L equals M equals J. Okay, so the automorphisms because they're maps. Okay, so counting the maps is the degree of the extension. This is going to be exactly the thing about permuting the roots of the Quintic. The number of automorphisms is the degree of the field extension. L over K splitting field of a separable polynomial over K. Because then it's normal. Right? Okay, I want exactly that text in my notes, I think. Not exactly that text. L over K splitting field for P of X, then separable. Separable polynomial? Yeah, that's what's going on here. L of K is the splitting field of a separable polynomial over K. Splitting field over K. Then the number of automorphisms is the degree. Number of automorphisms. So it's all about sending roots to roots. Okay. Counting those automorphisms. So there's a bit in the preamble about sending roots to roots, or moving the roots around, and this is what that is. Because the polynomial is preserved, I think, across the automorphism. Right, so 3.15, I mostly care about 3.15 with L equals M equals J. Catalan numbers. Oh, so I mentioned Catalan numbers quite a lot. They turn up in lots of different places. I'd like to know more about them. I think I know a bit about them, but I'd like to know a lot more. The answer to loads of different questions. If something turns up as the answer to several different problems, you've got to pay attention, right? The Wikipedia page on Catalan numbers is really good. So it's one of those rare occasions where the Wikipedia page on Catalan numbers is actually readable. Yeah, so Wikipedia/Catalan_number. That's not quite the link, but it's got some nice pictures along the way about all the different problems that Catalan numbers do, which is kind of good. Hankel matrices, you got loads of things. I've recently got a book which has got roughly hundreds of problems where the answer is always the Catalan numbers, which I'm looking forward to studying at some point, maybe on the stream. Who knows? Okay. Theorem 3.18. I'd be a finite field extension. Is this what we were just talking about up here? Oh yes, hang on. Using the previous thing. Finite field extension. Then the thing is finite. Finite field extension has a finite degree. The following statements are equivalent. Second assertion in 3.15. There'll be infinitely many maps. Okay, extensions from 3.15 up here. I did worry a bit about finite infinite around here. Second assertion. There's a map of K extensions. M to J. The number of maps is finite. Algebraic field extension. No, back in. Okay. Right. Following statements are equivalent. So if one, then the other. L over K is normal and separable. Fine, nice. Okay, using all those definitions that we had before. Normal. Can I remember what normal was? Something like the splitting. It's the splitting field for some polynomial. No, what was normal? Notes. Normal. Algebraic case of field association normal, even only it's the splitting extension for some polynomial. Good. Okay. And separable. That first one says that the image of K is the things that are fixed by, oh gosh, the automorphisms L preserving K. Oh gosh. And then 3, L over K is a splitting extension for separable polynomial coefficients in K. That's roughly what. Okay. The fact that it's finite is a consequence of the things we were just doing. We could obtain infinite ring maps, fine. And now these 3 things are equivalent. There's going to be loads of stuff to do this here. To show that P splits and is separable, so we're going from 1 to 2. So all these things are going to be equivalent. That's pretty hard. So that we could talk about these things being switched between the definitions here. Okay. Normal and separable. It's got something to do with being the splitting extension for a separable polynomial with coefficient of K. That sounds very similar to what it means to be normal. It's 2 to 3 easy. Let these things be generated L over K, and then multiply together them in all polynomials. Then that's the separable polynomial, and now L is a splitting field for P. Good, okay. So therefore, it's the splitting field for P, right? It's a splitting extension for that, given that it was normal and separable. So looking at 2 at the top of the page here. Generated L over K. It was finite, fine, okay. Finite degree. Let P be this. Take those minimal polynomials because it's separable. Check separable again. Really got to learn normal separable splitting. Normal separable splitting. Normal separable splitting. Separable was up here. Splitting extension. Normal. Finite field extension. Normal. If it was splitting, wait. Algebraic extension is normal. Finite field extension is normal. Which that means separable. And like algebraic field extension is separable if the minimal polynomial is always separable. Oh, so that's what we're doing. We're separating the minimal polynomials and then multiplying them. Good, okay. First by construction. 3 back around to 1 again. the image of L. Okay, right. Composition of an extension. Oh, I don't know, man. The extension is also a splitting field of a separable polynomial over L. Tautologically, the subgroup L. Look at this. Aut subscript L. There's a superscript. No, there's a subscript in my superscript, in my subscript, in my superscript. Okay. Aut down to L, up to aut, and down to L, and back up again to L. It's four levels. Aut L, aut K, L. The subset actually coincides with aut K, L. Oh, great. And then 3.7 counts them. From the tau and all that's 1, so these things are actually equal. What's the punchline at the end here? If L over K is an algebraic field extension, suppose L is generated by these things, and the minimal polynomial of each alpha I is separable, then the extension is separable. Okay, and this uses a whole bunch of technology from section 3 through the kind of quagmire of all the splitting separable stuff that I need to learn. According to dilemma 3.5 and 3.3, there's an extension such that the extension is the splitting field of a separable polynomial, and then use this rotator of 3 equivalent things. That means the extension is separable. So definition. Extension L over K is also separable. Hi, toast potatoes. Quest is going okay-ish. About to take a lunch break, so maybe this is a good time to pause. Okay-ish. Yesterday we had quite a good day exploring rings and modules. We did fun things like looking at different sorts of rings and fields, different sorts of domains. We have a lovely map of where we're going. Here's the lovely, lovely map. And yesterday we made great progress. We kind of looked at and understood a lot of stuff about ring theory. Today we're learning a lot of notation about different sorts of extension, different field extensions, which are marked on my map as a kind of lava pool and a swamp, kind of hard going, lots to learn. I'm hoping to sort of skim through the notes today so that after lunch I'm looking at Galois theory stuff, which I hope gives me more context around what's going on in the kind of definitional stuff. I've got a whole bunch of notes from this morning on notation, quick reflection back on the 3.5 hour live stream this morning. In these notes, we're using round brackets for field fractions. We have some sort of order stuff. We have some automorphisms. Group actions are going to be important. We defined some discriminant stuff. Or was it determinant or was it discriminant? I'm going to erase that and look it up. Some field extension stuff, and then we did loads of different types. My handwriting here is really terrible, but I've been learning really bad. Oh, hi Miles. Oh, it's Miles. All right, cool. Field extension separable. It's something to do with the minimal polynomial being separable, which means kind of no repeated roots. The irreducible factors have no repeatable roots. Separable polynomial, all the irreducible factors have no repeated roots. That's supposed to be the number. This is the ideal one, ideal generated by 1. And we have down here a simple extension, later about a simple extension. So I've got to keep in my mind the words separable, simple, and splitting, all of which start with S. A separable polynomial, separable extension. I've got a simple extension, which took me ages to understand at all. And splitting extension if the polynomial splits. So I've got actually kind of 5 things: separable polynomials, separable extensions, simple extensions, splitting polynomials, splitting extensions, and then everything after that involved a kind of random assortment of those 5 things. So it's gone a bit not my most successful Yesterday was one of my most productive mornings ever, and today less productive. I think I'm more stuck than I was yesterday, which is fun. Where I wanted to be. Normal extensions. I haven't even underlined the word normal. Where's the normal extension gone? I've got to tidy these up. Add break extension is normal. And then I've also got finite field extension is normal. Why have I written down both of these? Oh, this is a definition. A finite field extension is normal if and only if it's the splitting extension for a polynomial. So finite field extensions, which can be important. The definitions are very important. So you precisely understand what's going on. But I'm trying to. I genuinely think because of the way human understanding works, you can't just sit down with the definitions and learn the definitions. I've got to push through and get to other stuff. Right, see you around Mars. Have good luck with your physics test. Yeah, so I think after lunch I've got to push through to some Galois stuff, so that I start putting these concepts into like the correspondence, put them into more context. Or maybe this is already the context, right? This has already got like this counting thing about symmetry, counting thing about the automorphisms, which there are finitely many of them. Maybe that's my first clue that they're going to form a Galois group, and it's going to be fine. Counting them. Counting them is the first step of understanding them, I suppose. And I think the key thing is about tracking the roots and finding out where the roots go. And using the fact that polynomials, I think, are preserved, or polynomials kind of follow through. If you're preserving the field structure, then okay, then hopefully you're preserving the kind of polynomial kind of stuff, addition and multiplication. This was an incredibly complicated ring of proofs. How much of this do I want to write down? Kind of none of it, because I don't understand any of it, and I don't know how to convert it into a kind of note. Let's try and understand this last corollary. Let's read it one more time before we go for a break. L over K is an algebraic field extension. Everything's got a minimal polynomial. Suppose that L is generated by alpha 1 to alpha k, and the minimal polynomial of each alpha is separable. Yeah, so an automorphism is a mapping from a set to itself. Auto means same or alone or something, like on its own, and morphism is the kind of shape preserving way. I think the idea is that these things preserve certain properties. So if we're talking about automorphism as just as a set, then it means we take some elements and we just look at things you can do to shuffle the elements around. If we're looking at the automorphism that preserves like the ring structure or something, then we might look at the way to move the elements of the ring around to map the ring to itself, but maybe switching around different things. I'm trying to think of a good one on the complex numbers, but I'm really struggling. If you take the complex numbers and you do complex conjugation, so you replace I with minus I, and if you do that everywhere, nothing actually goes wrong. That's a field automorphism that takes the field of complex numbers and maps it to itself, and it's got something to do with what happens to the roots of x squared plus 1. Today has involved the three letters AUT quite a lot for automorphisms. But also seen in the word automobile, right? Like an automobile is something that lets you move around on your own without waiting for a bus. And also bus is a bus that you drive on your own? No, etymology breaks down there, I guess. Homework, learn the etymology of autobus. Is automobile really the thing that gives you independence? Is that the idea of the word? Etymology with James. Getting away from understanding this field extension. Suppose that L is generated by these things. The minimum polynomial of each is separable. Then the extension is separable. The extension is separable because that means that, go back to the definitions, go back to understand what it means for the extension to be separable. What are we trying to do? One more time. the extension is separable if the minimal polynomial is always separable. So it's kind of like, it's going to be, take anything and construct your minimal polynomial. So we're given all of these, given that all of these separable minimal polynomials, try and build a minimal polynomial of anything in that extension. 3.15 and 3.13, what were those? Let's quick look back. 3.15 was the county one. No, the finite one. And 3.13 was there exists a splitting extension. Back. Okay. So we've got this idea about separable extensions over separable things. I am going to take a break there. I'm going to come back at 1 o'clock in half an hour, roughly, to have a look at some Galois theories. That's right, we're going to get to Galois theory. And it's exciting in a way because we're only 20 pages away from, oh, it is not true, it's underlined over here, that's something to learn. We're only 20 pages away from the Quintic. So I'm hoping that the next bit, maybe this afternoon, excuse me, lets me plough through. If I make similar progress, lets me plough through to at least go and look at the Quintic from too much coffee. Go and look at the Quintic from the right direction to build up to it. Compute the Galois group. Yeah, okay. We've got a definition of a Galois group at the top. Yeah, we're going to come back for a field extension is called a Galois extension if, oh no. Superscript, subscript stuff. Yeah, okay. Field extension I from K2L. Thinking about it as a map. Yeah, okay. Drop the map I, identify okay with K, but only when it's done leads with ambiguity. That'll be nice. I would like that a lot. I would like that because I've been thinking about the copy of the real numbers that's in the complex numbers as just being like real numbers. Kind of not. Ashwin was off, and I'm off too. Are you going to miss some Galois theory? The VOD is... Don't watch the VOD. The VOD is going to be on this Twitch channel for a week, and on my YouTube channel, I think, if I can work out how to do that. So things do survive in some sense, but I don't think you should watch it. And there'll be more Galois theory later on. The aim is to eventually make a kind of explainer video to bring something back from the quest, right? Bring something back. So I've got something to show for my week of learning Galois theory. Hopefully some sort of simple explanation of what's going on. Good, right, okay. That's the end of this morning's live stream, I think. I'll see you in 25 minutes. The quest continues. It is to be continued.